Did you
Everybody.
hear from him?
Hey, Tim. How everybody? Anybody hear me?
Hello?
Yeah.
Can
Anybody
you
hear
hear me out there?
Hi, Gregory.
Yeah, we all got you loud and clear, 5 by 5.
Yeah. How are you?
Fine.
Good. Can everyone hear me?
Yeah, we hear you loud and clear.
All right, great. I'd like to introduce
How's the weather
myself.
down there?
I'm a new member, Greg Shanis. I was inspired by Craig McDougall, the assistant Jupiter coordinator. He's actually in my astronomy club in Tampa, the Mars Astronomy Club. And since then, I'd like to thank a few individuals that have been very instrumental. I went for the Mars award for the Astronomical League, and I sent 115 observations to Dr. Venerable. And Roger was very instrumental in helping me identify all the albedo features on Mars and also improving my imaging techniques. And then also Frank Maello, I've been in contact with, sending him some of my Mercury images, and he turned me on to what is Astrosurface? Yeah, that's a really neat project.
Yes.
Yeah.
Yeah.
And also Professor Doris Hill too. I have a YouTube presentation. I'm an avid meteorite collector, how to start a meteorite collection. And since then, I've gotten 3 emails from people all over the country. The latest one's from the Philippines. And so I bounce it off of Professor Hill, and, I tell them they're not meteorites, and she tells them they're not meteorites, and obviously they're disappointed and everything, but it's kind of neat. So this is a really good group of people, so I'm very happy to be a part of ALPO.
Yeah. So welcome. Yes.
Thank you.
While we're waiting here half a second, Mark Murata here. Did anybody else online right now? Did you know Walter Haas?
Yes,
Okay.
I knew Walter.
Who's that?
This is Matt Will.
Hi.
Yeah.
Matt, I worked with Walter for a year at the Physical Science Laboratory at New Mexico State University. I was taking some astronomy classes, physics. I was in the local aeronautics group, student club at the time. But Walter was so unassuming, he never told me about ALPO. I saw him 5 times a day, and he never mentioned it once.
Yeah, well, Walter was good. And sometimes I fall in that same trap. I just sent an email out to my own local astronomy club saying we have this annual meeting going on YouTube. You're free to attend. And sometimes it leaves my brain too a little bit. But yeah, well, Walter was a very unique mentoring kind of personality. And he was a wonderful person to know, and it was a perfect personality at the time to keep this organization together as it was back in the old days. But it's interesting, you worked with Walter out of the physical science lab then there.
Yes, that's right. That was back in 1978, actually.
Yeah.
Yeah.
Yeah, it's kind of a misnomer about Walter. Everyone thinks he taught mathematics at New Mexico State University. But
right.
he really was a civil servant, that applied mathematician that specialized in computer programming.
Right. Exactly. That's how I knew him. I worked in the computer center as an operations clerk.
Yeah.
Yeah.
Yeah, I was surprised when Walter told me that, because I always thought he taught mathematics. And I said to Walter in a conversation, "You were a card walloper, weren't you?" And he kind of chuckled and grinned and said, "Yeah, that's exactly what it was, man."
Yeah. Right. Good times. And I'm sorry that I didn't have a chance to interact with him. I did get to hear Clyde Tombaugh speak to the local student group.
Oh, wow.
And that was definitely a plus. And I got to, one of my projects was to use the Clyde Tombaugh Observatory, which was then on campus, to do some observations of Jupiter.
Wow.
But it was a long time ago, and it was a passing fancy then. And it's only been since 2014 or so that I've actually gotten active in astronomy, and really only the last 2 years, because I was very involved in some other activities that took my time. My telescope, you see behind me, spent 6 months in the garage twice back in the shipping cartons because I just never took it out.
Yeah,
So,
well, we all get busy.
Yeah. So anyway, this is
Yeah.
new to me, and I'm really impressed and happy to see that ALPO is still continuing. I was happy to be able to join.
So you knew some of the people there out of the astronomy department in New Mexico State University also?
Boy, I had to dig back through some transcripts to find those names. But yes, I have a Rob Ribald story about Ruth Beebe.
Oh, yeah, yeah. Uh-huh.
All right. Yeah.
Yeah, she spoke to us in 1993 when we had a meeting there in Las Cruces, annual meeting.
Okay.
And there are a few other names there that we were familiar with that had been with ALPO. I'm trying to think.
Yeah, like I said, I had to go back through transcripts. Girdicke, did you know Professor Girdicke in the physics department?
No,
Not
I did
an astronomer,
not.
but that's the only other person I knew.
Yeah. There was a Mr. Smith there too, and
Dr. August Miller.
Yeah.
Hello, everybody.
Well, it's 12 noon, high noon.
Yeah, just about, yeah.
Yeah, we'll get started in a few minutes. I just want to leave the door open for more people to show up.
Yeah, leave the door open. You wind up with 10 cats.
I can just remind everybody, please go on mute too after you log in, so we don't hear any extra noise in the background. Thank you.
Hey, Richard, Snooty. Richard,
Yes, Ken.
have you talked with Fred Pilcher to ask if they're ever going to participate in any of these conferences regarding minor planets?
No, I haven't. I haven't.
It would be a good idea because they do a lot of work, but you never hear from them, like in venues like this.
Yeah, I don't know what the deal is. I agree with you. Now I know Philip or Fred Pilcher, he's not 80, he's close to it.
I know, but there are, it's a very active session. There are other people.
Yeah.
Their Minor Planet Bulletin is something like 100 pages long.
Whoa, like the lunar
Yeah.
newsletter. Yeah, I don't quite understand what's going on there, Ken. But it's a shame because they do a lot of the work that I do, photometry. That's basically their thrust. I think Fred is retired and he's out in New Mexico. That's the last I heard.
Yeah, he moved out there from Jacksonville, I think about maybe 10 or more years ago.
Yeah, yeah. Of course, Daryl Nye has passed. He used to be involved with that.
Yeah, he was their distributor. I used to hear from Daryl when the tax man from Arizona would kind of calling, we have to use our federal ID to demonstrate that they were nonprofit.
Yes. Yep. Can't avoid the tax man.
Yeah, but if you're a nonprofit, you can skirt that issue of having to pay taxes on the periodical.
Yeah.
Want to have water, roads, infrastructure, you got to pay. That's just the way it is.
That's right.
Yeah, right.
That's right. You're right, Ken.
There's that Siri voice.
Yes. Let me get some coffee.
Tim, I'm having trouble with my video on mine. I'm going to have to go out, probably reload Zoom, and then come back in again. So I'll be back in a few minutes.
All right, no worries.
Okay, bye. See you in a few.
We'll give everybody another minute or so. We already have 9 people over on YouTube watching, and here on Zoom we have looks like 32. So it's a good start to the day.
Is that a cat or a
Really
baby?
is.
Is that a cat or a baby?
Somebody clicked on the wrong thing. That's last year's conference. It's like 32. It's a good start to the day.
Is that a cat or a
Really
baby?
is.
Hey, Tim, does my friend Jim cat or a baby talked to you or logged in or anything?
I have no idea.
Okay. I sent him the Zoom link a few minutes ago.
Whoever's playing the video, please go on mute. Somebody clicked on the wrong thing. That's last. All right, I think we'll get started. Before we get into the conference, though, I want to make an announcement. During the board meeting yesterday, we received some pretty sad news. Carolyn Shoemaker passed away yesterday. I'm sure a lot of you know who she is and have possibly even worked with her in the past. So I just want to start this off and with a tribute to her, and I want to open it up to anyone that would like to say a few words about her.
So if it weren't for Carolyn, I'm not sure what my career would have turned out to be. As an undergraduate attending the University of Arizona back in the very early 90s, got there in 1991, I met up with a fellow student named Tim Spar, and we both shared an interest in comets and particularly wanted to discover comets, and found out that there was a small telescope, at the time it was a 0.4 meter, the Catalina Schmidt, that wasn't being used. And we had known that groups like Carolyn and Jean's group, as well as Eleanor Helene's group, were using similar sized telescopes to discover comets. So one day off from school, I want to say it was Veterans Day, 1992, Tim and I drove up to Flagstaff, spent a day and night at the Shoemaker's place. And they basically taught us how to observe, how to discover comets and asteroids with photography. And I still remember the greatest thing about that visit was, at the time, I think Carolyn was the one who actually looked at the films. Jean would take the films, usually with David Levy, who's a ex-ALPO comet section recorder, as well as a few other observers. But it was Carolyn who was there at the stereo microscope discovering the objects, the asteroids and comets. And by that time, she had discovered at least a dozen, maybe more. And I remember her taking each image out and just showing them to us as if they were like baby pictures or pictures of her children with the stories behind each and every one of these discoveries. And I'll always remember that. So I'm always grateful to Carolyn. And basically, I mean, if it wasn't for her helping, as well as other people, maybe there wouldn't have been a Catalina Sky Survey, because ultimately those efforts turned into one of the best, if not the most prolific, comet and asteroid discovery survey.
Two questions. I don't know if Jean Carolyn had children, and also was the cause of death just that her body gave out, or was she caught up in COVID? Does anybody know?
All I've seen is she passed away at her home in Flagstaff yesterday.
If I could just say, I'm very sorry to hear this news. I did meet her a couple of times at conferences after the famous comet crash due to Comet Shoemaker-Levy 9, and she was always very, very gracious and interested in the amateur work that we were doing, and very happy to see the collaboration between amateurs and professionals over that fantastic period. So I'm sure she was a wonderful lady, and I'm sure she'll be much missed.
I believe I met her and her husband, David Shoemaker, up in Canada. And I can also remember when her husband passed away, he was, I think he got into a car accident out in Australia. And of course, you know, they drive on the left side of the road. I don't know. So anyway, but yeah, I echo what John just got through saying. She seemed to be very gracious and interested in our work.
Yes, I met Carolyn Shoemaker at the NEAF, stand for Northeast Astronomy Forum, a few years back, and I think she was the keynote speaker, and she gave a wonderful lecture. She had a standing ovation at the end. That's something incredible what she had, been doing it with her husband Eugene, and of course the highlight was to discover a comet in 1993 with the comet Shoemaker-Levy, but she gave an excellent talk, and I have a chance to say hello to her, and she was very pleasant, very friendly to talk to carry on that conversation. So that was just one time I met her.
Anybody else? Okay.
You must have met her, Tim.
Yeah, I did. I met her and Jean, I think a few times out here. One time, I believe at JPL. They're a great couple. I mean, they were the dynamic duo. They really were.
Tim, I'd like to add something. There was a meteor outburst this morning, which is probably a nice little tribute to her. And if she had anything to do with it, thank you very much.
Very good. Very good.
Oh.
All right. Well, thank you for that. She definitely meant a lot to this community. All right. Day 2 of the conference. I want to thank those of you that it's your first time showing up here. Thank you for joining us to this annual conference for the Association of Lunar and Planetary Observers. For those of you over on YouTube that are watching, thank you. I hope you enjoy it. The comment section is opened over there, and I'm periodically peeking over to see who's on and what we have going on. We have people from France over there, I see as well. We have currently 13 people on YouTube. And if you are over there, please hit the subscribe button and that little thumbs up button. That brings people to our YouTube channel and it'll really help us out. Thank you. Also, I want to remind everybody once again that on Zoom, please be muted during the presentations. There'll be time for questions following every single presentation. So you can ask your questions at the end. At the end of today, after we take a short break, we will be having our annual awards presentations and also door prizes. And to be eligible for the door prizes, you need to be a registered participant of the conference. And the way you do that is just send me an email. Obviously, if you're on Zoom, you've already done that. And if you're over on YouTube, just drop me an email and you will be registered. The only condition of that is people that win have to be residents of continental United States. So we can't ship things
What
outside.
about Hawaii or Alaska? Does that count? Seriously?
Show of hands, who's from Hawaii and Alaska?
I would say it does, but that's just me.
Well, we will check on shipping and we'll see if you want to pay for it. All right.
It's the shipping cost that is the problem. Yeah.
Tim, one question. Do we need to, when somebody's giving a presentation, you would need to reduce the video, to reduce the bandwidth or what? To eliminate the video, to mute the video?
I don't know what video you're talking about.
Well, I mean, somebody giving a talk, and sometimes when a lot of people on a video, reducing the bandwidth. If somebody just reduce it, probably will run much better.
I don't think so. I don't think so.
That's what I normally do sometimes.
Okay. All right. Well, if it works for you, then continue to do it.
No. Okay.
All right. Just go on the door prizes we have. From Celestron, they donated a Next Image 5 solar system imager. It's valued at $175. Explore Scientific donated a 6.5 millimeter eyepiece valued at $270. Alberto won last year, but he's the reason we have continental United States rule in there now because he lives in Argentina, and to ship his eyepiece would have been more than the cost of the eyepiece. So he's donating back the Explore Scientific 8.8 millimeter eyepiece, and Sky Telescope has also donated 2 field maps of the moon. So that's what we have going. And like I said, to be eligible, you must live in the continental United States. We'll add Hawaii and Alaska in case someone from Hawaii and Alaska wins. And you have to be a registered participant of the conference. And with that, anybody have any questions before we get started?
Tim, you've got my talks from Uranus and
Yes,
Jupiter,
I do,
right?
sir.
Good.
Yep.
Hey, Tim, just double checking you've got my Saturn one too, right?
I've got them all sitting right here.
Very good.
Yes, sir. Thank you. Great.
All right.
You're on top of it.
I'm trying. It's like juggling bunny rabbits over here. All right. First up today, we got Richard Schmoody. Was born in Washington, D.C., attended North Harris College, a country college, and Texas A&M. He received his doctorate in physical chemistry from Texas A&M University in 94. Since 94, he's been employed at Gordon State College as the professor of chemistry. He's a member of the Kingston Center of the Royal Astronomical Society. He's also a member of the ALPO and BAA. Richard has focused much of his research on measuring the brightness of the planets in visible wavelengths. And with that, let me bring up his presentation. Remote planets, that's the one, right? Yes.
The orange and yellow. Okay. Well, welcome everyone. Oops, I don't think that's it.
Oh, sorry.
Yeah, it's the previous one. You had it just a moment.
I don't know why this did this. Hang on.
Amateur.
Can't get good help nowadays. Where is it? What happened to it?
Free is good.
Oh, I know. Hang on. There it is. Let's do this one more time.
I know you haven't had any rain out there in California in a long time, but that backdrop really is something, Tim.
What backdrop?
The lunar surface.
Oh, that, yeah.
No.
Thank God for green screens. All right, let me see this one more time. Yeah. Share screen.
Okay, we ready now?
I believe so.
Okay. What I want to do is I want to talk about recent developments on the remote planets. Now, again, when I use the word recent, bear in mind, it takes Uranus 84 years to go once around the sun. So anyway, it's not like Mars or Venus that goes around the sun real fast. And I did become the coordinator of the remote planet section way back in 1990, a little over 30 years ago. And I decided to focus on photoelectric photometry when I did that. So anyway, and so this talk is going to summarize that, but also the very fine images that have been done, particularly in the last 10 to 15 years. So next slide. See, how can I advance this forward? Oh.
Tim?
Okay, there he is. Okay, just an overview of the talk. I'm going to talk about just one introductory slide. Then I want to present some images of Uranus. These are made primarily in red or near infrared light. And then I want to talk a little bit about brightness measurements and some of the fine work that Christophe Pellier did last November. And I think really what Christophe did is the wave of the future for amateur astronomy. And then I want to talk just briefly about future work. And I do want to stress in both of my talks, there is still lots of projects that the small telescope operator can do that will enhance our knowledge of the planets and the moon. So anyway, let's take a look at the next slide. Now, Uranus is tipped on its axis by 98 degrees. Now, this is what's going on. Uranus is actually tipped 82 degrees, but it's revolving in the opposite direction. So we say it's 98 degrees. It's sort of a mathematical thing. But basically what this means is every 42 or so years, the poles are facing the sun and the earth. And then about 20 or so years after that, the equator is facing the sun. Now here's what's going on. With Uranus, the equator faced the sun in late 2007. Its north pole is going to face the sun in the year 2029. So that's where we're heading. Uranus does move around the sun like the Earth, and we see different hemispheres. However, it's not like Mars where you can wait a year or a few months and see the other hemisphere. Uranus, you've got to wait several decades. Okay, right now, we're getting a really good view of the northern hemisphere, and the southern hemisphere, not so much. Maybe just the tropical portion of the southern hemisphere. And so, as I've said, the northern hemisphere is tipping towards the Earth. It will be at its maximum around the year 2029. All right, now in the next slide, I'm going to present to you three images. Take a close look at these. On the left, this image was made about 8 years ago by Damien Peach. Look at the top. You can see you got sort of a faint bright area here, but the very top is not filled in. Okay. Now go forward to 2017. Abukov took this image, and again, the top portion now is filled in. This is sort of the north polar hood. I've termed it that. And then if you go over to just a few months ago, Moron took this image, and again, you can see the north polar hood. If anything, it's a little brighter, but again, I can't say that for sure because I don't know how these people enhance contrast. So it's really, you have to be really careful with analyzing digital images. Now, before I move on, how many people have seen Uranus through the telescope? Raise your hand. Good, 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 good. All right. You know that generally speaking, it's a featureless disk. And that's because in visible light, the light that we see, Uranus has very low contrast. But if we had light or eyes that were sensitive to near infrared light, we would have a different view, and the views would look something like what I'm showing here. So again, these are different wavelengths of light than what our eyes are sensitive to. Okay, bear that in mind. Now, one of the things I've done is I've taken and I've measured the edge of this north polar hood, this southern edge, if you will. And I've been doing this since, I believe, late 2011. I had the first image there. Now, in this image here, I just measured the southern edge right down here. And I plotted it on a graph because I was curious, is this feature getting bigger? Is it getting smaller? And in the next slide, you can see what is happening. Here I've got the latitude of the North Polar Cap edge. And again, that's the southern edge. And of course, that's degrees of north latitude from 30 to 60 degrees. And on the horizontal axis, I've plotted the year all the way up to early 2021. Now, it seems to have been sort of constant until 2019. What has happened in the last 2 years? Seems to be getting smaller. In other words, its edge is moving further north, which means it's getting smaller. Will this happen for the rest of the decade? Well, we need to keep imaging Uranus and find out. So this is currently a project that we can adopt or look at and see what happens. All right. Now, switching gears now on the next slide, one of the things I've strived to do for about the last 30 years is measure the brightness of Uranus. Now, how long does it take Uranus to make one trip around the sun? Anyone?
84 years.
84 years. Very good, Ken. So a very long.
Carl.
Oh, Carl. Very long human lifetime, we'll say. So again, you're not going to get to see seasonal trends, say, in the next year. You've got to be patient. And so what I've done is I've used several different filters, particularly the V filter, which is sensitive to green light, and have been able to measure the brightness of Uranus. Of course, I have to correct for the changing distances. Okay, so V1 alpha accounts for the changing planet Earth and planet Sun distances. That way, I can compare a normalized magnitude for 2011 to today. And if there's a difference, it has to be due to the planet and not to changing distances. Okay, so again, changes in the V1 alpha value are caused by planet or sun changes. Now, the sun in visible light hardly changes at all. So I wouldn't expect to see a sun-induced change in visible light, but in ultraviolet light, that could be. The sun changes more in ultraviolet light than in visible light. And I believe as the wavelength gets shorter, the change gets greater from the 11-year sun cycle. Of course, Rick Hill probably can tell us more about that, I would suppose, or maybe. All right. And now on the next slide, what has happened? Okay, looking over this again, the normalized magnitude dropped or grew dimmer between 1991 and 2008. Now remember, the less negative the magnitude is, the dimmer the object. It's like playing golf. The lower the score, the better, right? But again, Uranus dimmed between 1991 and 2008. Now, what happened in 2008? I just said it about 5 minutes ago. What portion of Uranus faced the sun in 2008?
Northern?
What?
Northern?
Northern? Anyone else? The northern actually started facing the sun. You're right. But what's right in the middle of Uranus?
The equator.
The equator, yeah, the equator faced the sun. I believe it was very late 2007, maybe in 2008. And then since 2008, what has happened to the normalized magnitude? It has grown brighter. What does that tell you? Probably there's a seasonal change. In fact, it increased by about 7.5%. Part of this is probably due to the North Polar hood getting not only bigger, but brighter and filling in too. I showed you that in the image. However, there seems to be still some other causes that may be causing this because, again, we're dealing with the V filter, not the infrared filter, okay? Now, of course, as I said, the North Polar hood filled in between 2013 and 2021. Okay. Now, very recently, Christophe Pellier did the following. He recorded spectra of Uranus. He recorded images of that planet in the Johnson B, V, R, and I filters. And he used magnitudes, published magnitudes of Uranus from, I'm guessing, my paper or Tony Malama's work. And he was able to determine how much light the North Polar hood reflected and the amount of light that the areas further south reflected. Now, this is known as albedo. Let me give an example. Albedo is a fraction of light something reflects. So snow, fresh snow, might have an albedo of 0.8. In other words, it reflects about 0.8 of the light that falls on it. A piece of black coal might only have an albedo of 0.05 or maybe 5% of the light reflected by it. So again, he was able to measure the albedo of the North Polar hood in late 2020. And I want to summarize his results for the different filters on the next slide. All right. So again, albedo is a fraction of light reflected. So the higher the albedo, the more light that's reflected. Okay. Now the NPH is the North Polar hood. In the V filter, the albedo is 0.51. The North Temperate area, which is just south of the North Polar hood, it drops to 0.49. Not too much of a change, just a little bit. And that's why it's difficult to see the North Polar hood just through the telescope, because we're using visible light. Now, if you have a big enough telescope, you might want to try a red filter, and you might be able to see it then. It'd be interesting. I do know of one person who did glimpse the bright polar area. That's Rich Jekyll, very sharp observer there, very sharp eyes, but it's kind of difficult. Now, the near infrared filter, and I believe the peak wavelength is around 0.9 microns. The North Polar hood has an albedo of 0.13. That's pretty low, but the area south of it drops even further to 0.09. So as it turns out, the North Polar hood reflects something on the order of 50% more light than the North Temperate area. So that's why you're able to image the North Polar hood in near infrared light, even though it has gotten dimmer. The other areas have dimmed even more. And so it's interesting how things work. So again, Uranus is continuing to change in brightness, but again, patience is the key word here. It takes Uranus 84 years to make one trip around the sun. So a season is something like 21 years long. For Mars, it's something on the order of 5 to 6 months. So again, patience is the key for Uranus. Now, if patience is the key for Uranus, double patience is the key for Neptune. In the next slide, I want to talk about Neptune for a moment. Members of the ALPO remote planet section have been recording the brightness of Neptune since 1991. Actually, John Westphal did it a little earlier, but I couldn't transform his data. And then, of course, Wesley Lockwood out in Lowell Observatory, I believe he's retired. He's been doing it, I believe, him and others since 1950 or so. I believe there's others even before him. So we've actually got a pretty good streak of Neptune results now. But anyway, I want to focus on the ALPO work here. The brightness of Neptune was stable between, the beginning of this century to about 2018. However, it has dropped just a little bit since then. Now, it's going to be interesting, maybe more like 3% here. But it would be interesting to see in the next 10 years what happens. And again, with good CCD cameras or single channel photometers, we can detect these small brightness changes. Now, Neptune's southern hemisphere reached summer solstice about 16 years ago. So what has happened is the southern hemisphere is now experiencing summer, and the equinox will happen only 25 years from now. Mark your calendars. That's when the equator is going to face us. And of course, seasonal changes may be occurring on Neptune. I think they are. However, there are other factors. And again, I say that because between about 1980 and 1990, Neptune brightened by about 10%. That's a pretty big percentage. And of course, Lockwood and coworkers pointed that out. They're the ones, because I haven't started with Neptune until 1991. So anyway, some interesting detail there. Now, the future. In the next slide, I want to talk just a little bit about possible future projects. First off, we can monitor seasonal changes on Neptune. First off, with what I call whole disk brightness measurements. That means we measure the whole disk of Neptune or Uranus. And of course, imaging, particularly in different wavelengths of light. And then thirdly, very importantly, the brightness of individual features. There's no reason why we can't measure the brightness of, say, the North Polar Hood on Uranus, or the brightness of, say, a cloud that develops on Neptune. We can do that. We have the technology to do that now. Christophe Pellier has demonstrated that already. So I really believe this is the wave of the future here for planetary science for small telescope operators. That includes amateurs and college professors who have access to telescopes, say, 1/2 meter in diameter or less. So there you go. Future questions. In the next slide, I want to address a couple of questions maybe we can investigate in the next 20 years. What is driving the brightness changes on Uranus and Neptune? And again, geometry is part of it. The North Polar Hood for Uranus is part of it. I suspect there's other things going on, and we can use that now, or determine that now, using the technique that Christophe carried out last November. And one that I'm really interested in is the U filter brightness of Uranus and Neptune dependent on solar activity. I did write a paper a couple of years ago, and there seems to be a correlation between the sunspot number and the brightness of Uranus between 2014 and 2019. But again, I really would like to see more work here. Hopefully I'll be able to do some measurements this fall, and hopefully in future years too, and have a more firm question on that. Again, just on a historical note, back in 70 years ago, 1950-ish, the astronomers at Lowell Observatory were interested in, can we detect changes in the brightness of the sun by measuring the brightness of Uranus and Neptune? And I think perhaps we're coming full circle on that question. So anyway, that's all I have to say. I do want to thank the observers who have sent me work, particularly, next slide. I do want to thank those who've submitted observations of the remote planets, particularly in the last year. And I'm also grateful to Gordon State College for their assistance. In fact, I'm using a state computer right now to speak with you. So anyway, if you have any questions, I'll try to my best to answer them.
Yeah, Rich, yeah, good talk. You still recommended to monitor Uranus in near infrared with the near infrared filter, because that's involved in methane bands, and that make the contrast a little bit better to detect changes, right?
Yes, yeah, methane band photometry would be great. There's only one problem. My telescope is not nearly big enough to carry that out. And the methane band filter only allows in about that much light. My U filter or V filter allows in that much light. So I need to get a bigger telescope. Probably, I would say with methane band photometry, my guess would be I'd need probably a 1 meter telescope. That's just a guess.
Well, you can use the long band pass filter, like 600 nanometer long pass.
Yeah.
And from 10 nanometer to all the way to 1 micron, there's a lot of methane bands. And when there is some kind of outbreak in the atmosphere of Uranus, you can able to detect that the brightness changes. Because
Well, yeah,
the contrasts.
yes. Well, Christoph has already sort of done that with his work, and he's actually able to separate the two areas. Now, in my case, it would be difficult for me to do that. I don't have. First off, I've got talents, and I have areas that I don't have talents in, and computer type technology, I do struggle with that. So I'm going to be honest with you, and I'd rather let someone like Christoph handle that. And there's others. Some of you in this room, in this meeting, you've got talents, and what I want to say is I want to be the person that says we can still do work. I know one person, I have a lot of respect for this man, but he says amateurs can't do anything more. And I think I disagree with that strongly.
Who's that guy?
I would prefer not to say it on, but it's somebody that I have a lot of respect for, and I'm going to just leave it at that.
So Richard, is there any sort of corroboration from things like the Hubble Space Telescope in terms of the polar hood changing over the years?
Yes, the polar hood, the south polar hood, I believe it's changed too. That was back in the 90s and early 2000s. And I think I'd have to look at my book on Uranus and Neptune. I believe I've got some images of that, and I'd have to look at that. But the north polar hood, it started out just as a bright ring. Actually, I think it started out as nothing, and then there was a bright ring, and then the bright ring filled northward into the north polar hood. That's what I have seen on the images. But again, part of the problem is before, say, 2000, people were primarily just using visible light, taking visible light pictures. You really can't see this feature well in visible light. Does that answer your question, Jim?
Yes, sir. Thank you.
Okay, you're welcome.
Just a quick item, please.
Sure, Roy.
Hi, this is Roy Kalin. Just as a speculation, what would you imagine a seasonal change on Uranus to be like? Better mixing of the upper atmosphere, greater release of methane, a change of atmospheric pressure? Are those things, if you speculate on them, are those things that can be pursued at the amateur level?
I think so. I think a release of methane is a good one. The methane could be released, hits the upper atmosphere, turns into a cloud, and that's what may be causing this. And again, the methane band photometry, actually with the CCD camera, this is the way to go. The CCD camera, put a methane filter on it, and maybe take a little longer exposure. You need to go to good mount for this. I think amateurs could actually get some quantitative data on the brightness of the polar cap. Now, the only catch is you need to do some other things that are basically beyond the scope of this talk. I don't have a methane band magnitude, but I really do think we can do that. I mean, CCD camera, methane band filter. Don Parker had both of those items, and he did good methane band work with Jupiter and I believe Saturn. Julius can fill us in on that. But Uranus is the next one, and you don't even need a picture. All you need is to integrate the brightness, Roy, and you can get a quantitative brightness measurement.
Yeah, also that depend on the width too.
Yes.
Why did the methane band, the band pass, the more light will go through. I know that one filter have 10 milligram nanometer width, and that 18 nanometer width.
Yep.
And so the wider it is, the better chance to collect more light from your Uranus, because in order to increase the contrast.
But the CCD camera, I really think that's the way to go. And they're sensitive to that wavelength. So you're right, Frank. You're right. Yeah, and they do make different band passes for the methane band filter. And somebody like Damien Peach could probably do that, I would think. Did that answer your question, Roy?
Yes, it does. I'm just curious, is in any of these explorations in the different wavelengths, and any noticeable structure? For example, years ago, we learned of the hexagonal polar structure on Saturn. Anything that can be vaguely discerned on Uranus, or is it just featureless?
I saw this picture and it was at a science conference. I can't speak too much about it. You know, professional astronomers, they do work, but they have to be paid for it. Does that make sense? Amateurs don't. I saw an Earth-based image of Uranus. It had structure by one of the top 2 Uranus groups, I believe, in the world. As far as I know, this has not been published. It showed structure. But again, I can't go into it any further than that out of respect for this group, because I don't know if they received funding for this. They may have published it. I don't know. But again, my library does not get Icarus. And so I don't know if the image has been published. But I can tell you for a fact, yes, there's structure on Uranus. I was really shocked. But this image was better than what Hubble took, in my opinion. Yeah. I think it was with the Keck telescope. They probably used adaptive optics, and they probably used some kind of near infrared filter, possibly a methane band filter.
Okay, thanks.
You're welcome.
All right, anybody else?
Yeah, one more question, Rich. What's your prediction for the next 10 years on Uranus while the North Polar region start facing toward us? Now we're going to be just one bright disk and cannot see any structure. Is that possible?
That could happen. If you go back to the Voyager images of Uranus back in 1986, and that's when the southern hemisphere was facing us. And what you had there was you had kind of like a bullseye. You had a really bright center, but near the edges it got a little dimmer. That's what I think we're going to see. Now, that's one possibility. Now, if the North Polar hood continues to shrink, though, we may just see a bright circle and then a darker outer edge. It's interesting. I don't know. And now, invisible light, you're not going to see a whole lot. Remember that. Don't expect to see this invisible light. You need that near infrared camera. So, but it's exciting. I believe Uranus is going to continue to brighten. We'll see if that happens, perhaps by another 8 or 10%. And hopefully I'll be around to be able to see that and do that. My goal is to stick around at least until 2033. That will give me a half of a Uranus year. So I started in 91.
Thanks.
You're welcome.
All right, thank you very much, Richard.
You're welcome.
Very good. All right, our next speaker is Carl Hergenrother. Carl is the coordinator of the ALPO comment section, and effective last night at our board meeting, he's our brand spanking new executive director for the ALPO. So I'm looking forward to that. He's had on again, off again, mostly on again member of the ALPO since his high school days. I don't know if this is right, in the early 90s. Wow. In northern New Jersey. He has a BS degree in atmospheric sciences from the University of Arizona. Rather than entering the field of meteorology, he became an observational astronomer at the University of Arizona, where he mostly studied comets and asteroids. And he was a part of the Catalina Sky Survey with our own Rick Hill, where he discovered 4 comets and numerous asteroids. Carl spent most of the past decade as a part of the NASA OSIRIS-REx mission to acquire samples for the near-Earth asteroids Bennu. He his 2 primary achievements at OSIRIS-REx was selecting Bennu as the OSIRIS-REx target and discovering that the surface of Bennu is routinely ejecting small particles into space. With OSIRIS-REx time, Bennu, at the end, he's moved on to the Ascending Node Technologies, LLC, a small business specializing in spacecraft planning and operations software. Carl enjoys backyard observing, where his go-to equipment are a pair of Vixen 30 by 125 binoculars. And since observing Halley's Comet back in 1985, he's visually observed 135 different comets. And that brings us to Carl. Welcome.
Thanks for having me. Can everyone see my presentation okay?
Yes, sir.
Awesome. So I'd like to talk about the comet section. I kind of provide a general overview of a little bit of the history of the section, what are the goals of the section, the type of observations we're interested in, how to contact us, and give a rundown of pretty much the last 18 months of activity, all of calendar year 2020 and 2021 up till now. And as well as talk about a few specific comets of interest and give a look forward to comets that will be bright and observable over the short term, as well as even looking out to 2024. First, I'd like to give a big shout out and thank you to all of our comet section contributors. We've got quite a few people here who have contributed many images and magnitude observations and descriptions of comets. In particular, I'd like to call out, I mean, a lot of people have sent us a lot of data, but I would like to call out two observers in particular. Mike Olison, who just recently moved to the Tucson area, has been observing comets almost every clear night. And I'm always amazed because I live not too far from them and I've given up on nights. And then all of a sudden I get an email in the morning and there's all these images he took with his C11 going down to 19th magnitude of comets. It's like, yeah, I probably should have been out there as well. And Chris Wyatt, who's down in Australia, he uses a 16-inch Dobsonian. And almost every clear moonless night, he's sending me magnitude estimates for sometimes up to a dozen comets, which takes quite a bit of time to hunt these comets down, know you've really seen them, and then do your visual magnitude estimates. Oops. So the ALPO's comet section doesn't quite go back to the formation of the ALPO back in the late 40s. It started about 10 years later. With the appearance of comets Mercash and Aaron Roland, which were two of the great comets of 1956, 1957. And it was David Meisel, who at the time was an undergrad student, who really pushed for the production of the comet section. And it's interesting, if you look at the little write-up announcing that, you know, we have our first comet recorder in the journal of the ALPO, about how there was a hesitance to even form a comet section, because comets were neither lunar nor planetary. But comets do offer a legitimate and a neglected field to amateur observers. And during much of the first 20 years of the comet section, the ALPO comet section was the premier comet database and archive for comet observations. And the idea at the time was to, you know, create a section that would collect images as well as magnitudes and do analysis on it. And we try to continue that heritage, try to continue that tradition. And we do publish a monthly guide to which comets are observable in the sky. And I put those out on cloudy nights, partly as an advertisement to solicit more observers who are looking at comets to submit observations to the comet section, as well as to tell people there are comets. I mean, just because a comet is in the news, there's always a few comets out there that are within range of small telescopes. As for the section itself, right now it's the two of us. I'm the coordinator, but just recently, Michael Ikonik has agreed to be the acting assistant coordinator. And Michael is actually a retired nuclear engineer who lives in the south of France, and he does a lot of observing. He's even got a mobile observatory and does a lot of sketching. And that's something I really wanted to push, is to get more people who are sketching comets to submit their observations. And we collect all different kinds of observations. It doesn't matter what observation you have, whether it's a CCD image, it's a photography, it's old, it's new, it's a sketch, magnitude, spectra, or even just writing, I saw the comet tail was this big, it was fuzzy, a textual description. We accept it all. And contacting us is easy. Just send your observations to comments@alpo-astronomy.org. Now, a lot of the observations we get kind of fall into two categories: magnitude estimates, how bright does a comet look, and images. And we have a magnitude database that currently consists of over 14,000 magnitude measurements of over 400 comets going back to 1955. Since the 1st of January 2020, so over the last 18, 19 months, we've received over 1,000 magnitude estimates of 65 different comets from 11 different observers. And we do prefer it at the the magnitudes be submitted in the International Comet Quarterly format, which is has been the standard for about the last 30, almost going on 40 years now. But even if you don't have your observations in that format, that is okay. We will convert them for you. And the great thing about magnitude observations is not only tells you how bright a comet is at one time, which allows you to predict how bright it'll be in the future, but you get light curve observations. You can produce a light curve. You can detect changes in the brightness of an object. And sometimes these changes are due to outbursts. Sometimes they're due to the comet disintegrating and falling apart. So it's really important stuff. And there's actually very few professional astronomers who are actively involved in this work. There are a couple, but it's still amateurs that are producing, I would have to say, 99% plus of the magnitude estimates of comets out there. And that data is what the few professionals who do publish light curve work, they're actually using that amateur data. The second category is images and sketches. And this is kind of an example of 3 different kinds of images. We've got an image of the most recent comet, which is one of the most recent comets, Comet Nishimura. It's definitely the most recent amateur discovery, discovered only about 20 or so degrees from the sun, though it was Nishimura was using a CCD to discover this. You can see actually a nuclear jet rotation. So as the nucleus is rotating, there's a jet coming off the nucleus, and it's almost like, a water sprinkler as it's rotating, putting out jets. This is a NEOWISE from last year. And the images are more than just pretty pictures. For example, this center image here of one of this year's bright comets, Comet Atlas, which got up to 8/9 magnitude. As you notice, you've got the gaseous coma here, which is kind of in the blue-green. You got a bit of an ion tail, which is this very narrow, straight structure, which is going mostly antisolar. And then there are 2 faint but diffuse dust tails. And you can actually do an analysis where you can do kind of a dynamical analysis on the motion of cometary dust after it's been released from the nucleus. And based on the time of release, as well as the size of the particles, you can take an image like this and actually figure out, okay, this material that's going this way, which is kind of going in the same direction as the gas tail, is actually rather light material released recently, quickly being blown back by the sun. While this other kind of fainter, broader dust tail over here is actually larger particles that are moving much slower away from the comet itself. They're lagging behind the direction of motion of the comet. The comet's moving this way from a little bit upper left to a little bit lower right here. And these are actually particles that were released many weeks or months before this image was taken. So you can do a kind of like a forensics analysis, looking at the dust of a comet, figuring out what the activity rates were going weeks, perhaps sometimes even months in the past. And later on, I'll talk about a really cool discovery that you may have read about in the news, where you can use the same sort of analysis and determine that the comet had been active for decades prior to discovery. So sketching is one thing that a lot of people, there are still people out there who sketch comets. They go and visually look through the eyepiece and they sketch them. I did notice when I took over the comet section a few years back that I was not getting a lot of sketches. It seemed like if I was getting images, they're all CCD images. And so I did have to go reach out to a few observers and just, especially on cloudy nights, and say, send your observations in. And I think a lot of people, and you have the same problem, I think, with the other sections like Jupiter and Mars, where people who are sketching feel like they can't quite compete with the CCD images. Now, I love sketches because, for one thing, it kind of shows a better representation of what the comet looked like when I looked through the eyepiece and saw it. But also just to kind of show how good the eye is. These 2 images were taken only minutes apart, one by Gianluca Massi in Italy, and this is our acting assistant coordinator, Michael, in France. And this is a short period comet 46P Vertinen. And what you see here is that Michael visually was seeing the same structure that Gianluca was pulling out in his co-added deep and processed CCD image. So these features are real, and they were confirmed by CCD imagers. So as I mentioned before, we collect all observations, and all observations are worthy of submission. And when I do reach out to observers and ask them, would you be willing to submit your observations to the comments section? I almost always hear the same thing. I didn't think my observations were good enough. And I understand that. I observe comets all the time. I submit my own observations to the section. I do occasionally observe planets. And I even now find myself going, well, I should submit this to like the Venus section, but they're not very good. They don't compete with everyone else. So I understand the feeling that your observations may not be worthwhile, but all observations are. It's very possible that an observation you took of a comet, you were the only one looking at that comet at that particular time, perhaps the only person looking at that comet that night. So that observation not only fills a gap in our coverage, it might be the only observation noticing something new on the comet. Comets are very dynamic bodies. So it's possible you were the sole witness to a particular event. And while not everyone can take images that are aesthetically beautiful, I mean, images over here, that's what the comet looked like, either naked eye or through small binoculars or a small telescope. So I always like, as much as I like these comets, these images, and I really do, and I wish I could produce images as good as these, I do like looking at pictures that show what the comet looked like to the average observer under average observing conditions. And so we take these images and sketches and we put them in our image gallery like all the other sections. And we currently have over 6,000 images of over 600 comets. And in 2020, we received about 500 or 600 images and sketches of close to 60 comets from 37 different observers. This year so far, we've had a little less, mostly because the year is only half, but also we haven't had a great comet yet, or even a really good comet yet this year. But we've got close to 300 images of 75 different comets from 37 different observers. And the other thing that we've only had a few submissions, and in fact, this is probably what you're seeing here is about 40% of all our spectroscopy submissions. But one thing I do want to advocate for is more spectroscopic observations. And either as simple as just having an objective prism in here, like this image from Chris Shore, and you can use like a star analyzer, the star analyzer 100, 200, stick it in your filter wheel, and you do get a breakdown, low resolution breakdown of the various species that are glowing within the coma and tail of a comet. But if you have a spectrometer, you can go into much more detail and you can actually get data that you can then actually measure the production rate of each of these individual molecular species. So instead of just measuring how bright a comet changes over time, you can actually measure how the CN levels increase or decrease, how the water levels increase or indirectly, the OH levels directly, and then the water indirectly, how these levels increase and decrease. So there's a lot of interesting work here. And yes, you need, even with a reasonable sized telescope, you're probably limited to the brighter comets, but there's still a lot of great work here. And there's a lot of comets out there and the professionals can't keep track of all of them on every night. So there's still a lot of work that needs to be done by amateurs. And that includes even the magnitude estimates, which can be done visually with binoculars. There's a lot of work that you can do just from your backyard that really helps comet science. So for the comets that were observed over the last 18 months, the brightest was, of course, Comet Neowise, which happened last summer, got up to about first magnitude. We had a few other comets that were borderline naked eye, 5th, 6th magnitude. While technically you can see a 5th, 6th magnitude star naked eye from a dark site, diffuse comets a little harder to see. We had close to 16 comets or 17 comets that got brighter in about 10th magnitude. Neowise by far produced the most submissions and images and magnitude estimates to the ALPO, with 2 comets that which I'll talk about in a little more detail in the next slides, 2019 Y4 Atlas and 2020 F8 Swan coming not too far behind that comet, behind Neowise. So last year, at last year's annual meeting, I discussed in more detail, in fact, almost the entire talk was about Neowise. So I'll just kind of do a quick summary of what we saw with Comet Neowise. While probably not the great comet of 2020, at least visually, it didn't have that impression. It didn't, at least to my eyes, was nowhere near Hale-Bopp or Hyakutake. You could have called it the really good comet of 2020. And definitely for us here in the Northern Hemisphere who weren't able to see Comet McNaught back in 2007 at its best under dark sky, and weren't able to see Comet Lovejoy back in 2011 at all. This was definitely the best comet since Hale-Bopp back in the spring of 1997. Peaked at about first and second magnitude in early July, though at that time it was located deep in the glare of dawn and was a little difficult to see. Though by a week after that, second week of July, it did come up. It did move out enough where you could observe it even if it was a little fainter. And just these are some great pictures here of the rising tail, like a searchlight beam. And I remember observing it through 30 by 125 binoculars. And that is what it looked like as it was rising above the Catalina Mountains here. And even this image here by Gianluca Massi, and that's St. Peter's in Vatican City. Here's a comet cutting through the light pollution of Rome. Of course, when you're in deep twilight, it doesn't really matter about light pollution because you have natural light pollution from twilight. So that the comet can cut through twilight. You can see it anywhere, even from the middle of, say, New York City. And observers were able to see sort of this bifurcated tail feature, which seems to be common for comets, especially comets that get very close to the sun. Up here, this kind of a stock photo I have in my background, that's the Great Comet of 1881, which also shows this bifurcated feature here. And the thinking is that you have a nucleus, it's throwing out dust. The dust is mostly going out almost in a shell. I can even use my glasses, a better example. And what you're actually seeing is when you're looking through the areas of maximum density. And those on the edges of this shell coming off, this dust shell coming off the nucleus. And that's why you kind of get that bifurcated feature there. By mid to late July, the comet had moved well away from the sun and was located, by then it had even moved into the evening sky, it was located in a dark sky. And some of the astrophotographers, this image in particular, where we got the Big Dipper kind of for reference, we're detecting tails as long as 30 degrees for the ion tail and 10 degrees for the dust tail here. And again, you can see there's the dust tail is curved in different directions, and you could use a Finson-Probstein analysis like I showed on that previous slide and determine exactly the size of this dust as well as when it was released from the nucleus of the comet. And we lost NEOWISE at the end of September. It again moved too close to the sun. This time it wasn't first magnitude, it was more like 9/10 magnitude. So it was lost to most observers. And interestingly enough, even though it has been observable or should have been observable in the dark sky going back to at least this spring, only one observer, and this is the Pan-STARRS Near-Earth Asteroid Survey, which uses a 1.8 meter telescope in Hawaii, has observed NEOWISE. And they had picked it up at 22nd magnitude. So it faded pretty quickly from the time we lost it in late September through this summer. And also just to show a good example of the observations, the magnitude observations submitted to the ALPO comet section and how well we can model it. So the two comets I kind of teased before, Atlas and Swan, were two comets that prior to NEOWISE were supposed to be the big comet of the year. Atlas, there was a lot of hype in the media about this being the comet of the decade, comet of the century, as bright as the moon. It was interesting that the comet actually shares the same orbit as the Great Comet of 1844. It was forecast to reach at least 0th first magnitude, but unfortunately it peaked out at 7th magnitude in April, kind of stalled. And then as you can see from amateur observations, broke up into some pieces, and then Hubble was able to observe it and saw the comet nucleus had completely fallen apart and disrupted, which is something that commonly happens to small comet nuclei making their first approach to the sun or close to the sun, as well as what may have happened is this is a piece that fell off of a larger comet in the past, and those smaller secondary pieces often are unstable and fragile and will disintegrate, if not during the initial return where it broke off, later on. And one great thing about this comet was it was one of the best placed and best observed disintegrating comets we've ever seen. And because this happened in April 2020, almost every professional observatory was shut down due to COVID. Hubble was different. Hubble was active, but other than that, whether it was the U of A observatories, U of Hawaii observatories, ESO, University of Texas, all shut down. So it was amateur observations that actually did 99% of the monitoring of the breakup of this comet. And then we had Comet Swan, which, boy, it was looking really good inbound. And people were getting excited, thinking this would get up to 3rd magnitude. Even had an outburst up to about 5th magnitude. And then again, it just started getting fainter and fainter and fainter. And this image here showed the comet not too far from perihelion, and it's showing the telltale sign of no condensation and just kind of smearing out as the nucleus had fallen apart. And we didn't just have long period comets over the last 18 months. We also had the brightest of the short period comets observable, which was 88P Howell. This was a comet discovered in 1981, making its 9th observed return. And this one routinely gets up to about 10th magnitude. And this year it got up to 8th or 9th magnitude. And I always like pictures where a comet photobombs a nice deep sky object there. So looking forward, we do have 2 objects which could be bright, could be interesting. They also could turn out to be nothing. So one is C2021 A1 Leonard. This was discovered by Greg Leonard at the Catalina Sky Survey. First comet discovered of 2021 was 19th magnitude. Kind of an interesting observing geometry. It approaches to within 0.23 AU of the Earth on December 12th of this year. Unfortunately, it is kind of interior to the Earth, so it's almost directly between the Earth and the Sun. That's when a phase angle is at a maximum on December 14th. So it's only going to be about 15 degrees from the Sun at the time, similar where Neowise was when we first located it. It comes even closer to Venus at 0.03 AU a few days later, and perihelion is in early January. That high phase angle may result in a brighter comet due to forward scattering of dust. If you've ever looked at a projector beam or even a shaft of sunlight coming through a window, you'll notice that you can see the dust in that sunlight. And if you're looking more directly in the direction back up the beam, that dust is brighter. That is forward scattering due to that dust. So this is a comet which, if there were no forward scattering, should get up to 5th, 6th magnitude, but could get 2 to 3 magnitudes of enhancement. So maybe it'll be a 2nd or 3rd magnitude. But again, it's really, really close to the Sun, unfortunately. So it's going to be a horizon hugger for the Northern Hemisphere, a little better from the Southern Hemisphere. And then unfortunately, we lose it post-perihelion as it goes south of the Sun. So this is an object that could be like a Neowise, but in considering the fact the comet's been slow to brighten, it might not even be visible when it's that close to the Sun, unfortunately. And then another comet just recently discovered, as in a few weeks ago, 2021 O3 Pan-STARRS, is also similar. It'll get very close to the Sun, 0.29 AU on April 21st of next year. Also gets a high phase angle, which may result in 1 or 2 magnitudes of dust scattering enhancement. But it also will be located pretty close to the Sun. And so the Southern Hemisphere will have the best shot at seeing the comet near perihelion. Though again, it'll be 15 degrees from the Sun. But for the weeks afterwards, the Northern Hemisphere will be able to see in a darker sky. Though by then, maybe it'll be 6th, 7th magnitude. But these are 2 comets that we're going to look forward to in the coming months. And then this comet will I shouldn't say definitely won't be a visual object in 10 years when it comes to perihelion, but could be. And this is comet Bernardinelli Bernstein. And I love when comets are named after people rather than surveys. And this object was discovered in data going back to 2014. It's kind of looking back through old archival data. And it was discovered when it was 29 AU from the Sun, which is the distance of Neptune, or comparable. It's currently 20 AU from the Sun, which is around where Uranus's distance is. And perihelion doesn't occur till 2031, when it'll be a little further from the Sun than Saturn gets. And it could peak as bright as 12th magnitude, or it might only get as bright as 16th magnitude. We shall see. But it was in the press a lot because a lot of people were talking about how exceptionally large the nucleus is, though a lot of those estimates were done before we realized this object was an active comet with a coma. So I'm sure the nucleus actually is quite a bit smaller, but it still must be a large comet to have been observed that far out and to have been active at distances beyond Neptune. And this is actually my last slide, just going through other comets expected to be brighter than, say, 9th, 10th magnitude. We do have quite a nice assortment of short and long period comets. 2024 is a little interesting because we'll have 2 Halley type comets, Pons, Brooks, and Olbers returning for the first time since the 1950s, which is about the exact same years that the ALPO comet section was created. So that'll be a nice little, I guess that would be 70th anniversary present for the comet section. Questions?
Would you define what you consider to be small aperture scopes?
So for visual observations, I use the smallest aperture telescope I can definitively detect the comet. So I like binoculars, and for comets, it depends how dark your sky is. 7th, 8th magnitude comet, 10 by 50 binoculars, great. So you can use things small. For imaging and photometry, again, I find that the observers, and this is also from personal experience, that produce the best magnitudes are using the shortest focal length telescope possible to detect the object. And so a lot of them are using short focal length refractors, 80 millimeter, 100 millimeter. So you can do a lot of work with just small telescopes. And the thing with CCDs, of course, which is great, is that even if a comet's faint and you've got the time, you can co-add hours of observations and go significantly fainter with a small telescope.
So with an 8-inch Newtonian, in a suburban sky, I'm in Atlanta, well, east of Atlanta, I do not have streetlights, but there is residual light pollution, but it's not terrible. So with an 8-inch Newtonian, what would you estimate that a limiting magnitude, or as far as comets go, I should even expect to try and see?
I mean, usually the rule of thumb is you can go determine your stellar limiting magnitude and then subtract 2 from that. And that'll kind of give your cometary limiting magnitude. It depends on the comet. If it's like, Comet Vertinen, which got really close to the Earth and it was a short period comet with big gassy tail, sometimes the comets can get so big and diffuse that you don't see them.
Right.
Right. But in general, I'd say 2-3 magnitudes off of your stellar limiting magnitude, you should be able to detect. So I know for my binoculars, I can get down to 12th magnitude, maybe 13 stellar. Darkest conditions with total dark adaptation, I can get down to 10, 10 and a half.
Hi, Carl. Yeah, great talk. I just want to mention, while you were showing all the upcoming comet attraction, what is the best comet it's showing in the sky right now?
Right now. So 2021 has been a little bit of a bummer year in that we really haven't had many comets brighter than about magnitude 10. And currently the brightest comet in the sky that is easy to observe is C2020 T2 Palomar. And that's still about magnitude 10 and a half or 11. So coming up later on in the fall, 67P Churyumov-Gerasimenko, which of course we all remember, that's the Rosetta mission target, is making its first return since Rosetta was there. And since Rosetta actually crash landed, soft landed on the surface. And that will be about 8th, 9th magnitude. And Comet Borrelli's coming back, which was another spacecraft target in January. That object will also get up to about 9th magnitude. But it's those 2 long period comets I talked about, which might be 6th, 7th magnitude in a dark sky. Time will tell.
Carl, I have a question. I wrote in the chat, is the distinction between centaurs and comets clearly defined? We noticed that this comet has a what we call a coma, and centaurs are presumably too small to have atmospheres. And yet we wonder how many of those centaurs were originally comets and so on. What do you think?
So I actually personally see no distinction between comets and centaurs. Short period comets we know come from the Kuiper belt, really the scattered disk part of the Kuiper belt, where Neptune's gravity and the other outer planets are scattering these objects out of the Kuiper belt disk, and then they're slowly moving in to the inner solar system to become short period comets. Centaurs are really just objects that are kind of halfway between that cold reservoir in the Kuiper belt and close to the sun, what we call Jupiter family comets. So they're sort of transitional objects, but they're still comets. And in fact, there are a lot of centaurs that have been observed to show cometary activity. In fact, it seems like almost every centaur with a perihelion distance within about 9-10 AU has shown cometary activity, and the ones beyond that haven't. So even for those centaurs that don't show cometary activity, they may have in the past, maybe it's episodic, or maybe they just haven't gotten close enough to the sun yet. But they're all comet nuclei, and hopefully one of these days, one of these 50, 100-kilometer centaurs will get kicked into the inner solar system, and we'll have a comet every 5 years. That's naked eye.
Can I ask? I was very interested in what you said about 2014 UN 271, because I wasn't aware that it had shown cometary activity. But has any other object been seen to show such activity at such an enormous distance? And how big would you estimate that it actually is?
Right. So we have seen comets on the way out show activity out at those distances. Hale-Bopp, last observation of Hale-Bopp, and it was about, I think, 23, 24 AU out, was still active. A lot of comets now, like Comet Ison being a perfect example. Remember Ison, yet another comet of the century, which didn't produce back in 2012, 2013. When it was breaking up, as it was going through those SOHO chronograph images, Zdeněk Sekanina was able to model the dust tails as it was going close to the sun. And using that Finson-Probstein analysis that I showed before, came out and said, the only way you can get dust on some of these trajectories is if it was released 20 to 40 AU out. A comet that I have that I didn't talk to in particular, because I will probably be talking a lot more about it at next year's meeting, is C2017 K2 Pan-STARRS. And this is an object that might get up to about 6th, 7th magnitude when it's at its brightest 2022 timeframe. That object also was discovered pretty far out. Pre-discovery archival images were found extending it out even further. And again, using Finson-Probstein analysis of the dust we're seeing suggests that it also is active out at 20 to 30 AU.
Wow.
So it does look like some of these comets, especially first time coming in, because you got volatiles, which haven't burnt off, like carbon monoxide, carbon dioxide and such, methane, ammonia, you can have activity very, very far out.
Do you have any suggestions for what filters would be useful for imaging comets?
Yeah. So a lot of time for just, if you want to do photometry, a V filter, or even just a green filter, it doesn't have to be a photometric, V filter, gets pretty close to what the eye sees. It's not perfect, but it gets close. And so that way you do have a good representation coverage of the gas and the dust that the human eye sees for magnitudes. A lot of comet photometrists use very specialized narrowband filters that isolate individual comet species, like NH+, like the various swan bands. Those filters are expensive because they're very niche, and only really professionals can afford, the thousands and thousands of dollars sometimes per filter for those. But if you observe in a blue filter, you mostly are getting gas. If you observe in an R filter, you're mostly getting dust. And V kind of is in the middle, and that's what the eye sees. But there are people now who, they measure something different than just the magnitude of the comet. They measure something called AF rho, which is kind of a way of trying to more physically determine the production rate of dust. And for that, you want to observe out in the red. I filter would be best. R filter is okay. But you want to observe at band passes that don't have a lot of gas contamination, where you're seeing almost purely dust. But comet photometry and filters, it's complicated.
Is there any evidence from spectroscopy or filters that there is a change in composition indicating layered structure in comets?
There hasn't been a lot of that, though I do know Comet Hartley 2, which was observed by one of the NASA missions, and I'm blanking on which one. That comet showed a kind of bimodal structure. It was almost like there were two pieces kind of glued together. And this seems to be a common structure among some comet nuclei. And it was interesting because as the spacecraft flew by and was studying it, one of these lobes, bodies, masses, it was producing different molecular species than the other at different abundances, almost as if either the comet was not homogeneous, and so one was richer in something in species than the other, or it's possible that these were two separate comets that then merged together when they were out in the Kuiper Belt, because things are moving much slower out there, and you can actually have collisions that are slow enough that rather than completely destroy an object, they kind of just accumulate and attach to each other. So we did see something with a comet Hartley 2, which suggested that the two components that are part of its nucleus may have had different origins, may have been separate bodies in the past.
Yeah, Carl, there's just one more question about the Halley's Comet. We haven't heard that in a long time. Right now, it's closest to aphelion, the further point away from the sun. So, now
I think that's going to be it's coming up in a few years. I think it'll be at aphelion. I can't remember exactly.
All right, yeah. Then after that, it's on the way toward the inner part of the solar system. Then you got to wait another 25 years for that.
Yeah, 2061. It should be a better return than 1986. As we all know, 1986 was the worst return of the last 2,000 years. This one in 2061 won't be great, but the comet will be mostly between the Earth and the sun. So you'll have forward scattering with dust. Yeah. So it should be more of a 0th first magnitude object for a few weeks.
I think there was an article in Sky Telescope in June or July. Joe Rayo.
Yeah.
He's the author. He's a good friend of mine, and he talks about comets, and he analyzes what the comet will look like 2061 compared to other apparitions.
Yeah.
It's very interesting to find out.
Yeah, that was a good article. I really enjoyed it. I'm always happy when I flip through my Sky and Telescope and I see a comet picture or a comet article. Makes me happy.
All right, that was very good. Thanks, Carl. We're running a little bit behind, so we want to jump ahead. We go from the incoming executive director of the ALPO to the outgoing executive director of the ALPO, Julius Benton. He first became interested in astronomy at an early age. He got his first telescope, a 4-inch unitron refractor. After several years of looking at the night sky, he began to specialize in lunar and planetary observing. Those interests led him to join the ALPO in 1967, where he became the coordinator of the Venus and Saturn sections in 1971, and has continued to manage these two sections for well over 40 years. A longtime member of the ALPO board of directors, he's served several terms as executive director, as a life member, and he's also received the Peggy Haas Service Award and the Walter Haas Award, commemorating his many years dedicated to the service of the ALPO. Board member, executive director, consecutive years. Let's see, I already said all that. Okay. As numerous articles have appeared in the Sky Telescope, Astronomy, Journal of the VAA, Journal of the Association of Lunar and Planetary Observers, Star and Sky, and elsewhere. Besides his interest in lunar and planetary observing, Julius is an avid outdoor enthusiast, long-distance backpacker, and a life member of the Appalachian Trail Conservancy and American Long-Distance Hikers Association. Wow, I did not know that. Welcome, and looking forward to your talk on Saturn.
Oh, Julius.
Are you out there, Julius? Gotta unmute.
Can you hear me?
Yep. You're good.
Okay, this covers the 2021-22 current apparition. of planet Saturn. The next slide. Okay, I always like to open my presentations to bring the guiding principle of the ALPO that was established by the late Walter Haas back in 1947 to encourage and coordinate regular systematic investigations of our solar system with instrumentation readily available to amateur astronomers. That's expanded a lot these days with new technology, spectroscopy, CCD imaging, and so forth, but a lot of those types of instruments are becoming more available and not quite as expensive as they have been in the past. Okay, next slide. Okay, the value of Saturn observations. Amateurs are free to observe at their leisure for extended periods of time, weather permitting. Systematic observations provide long-term records for further study by the professional community. We often have many professionals that have come to the ALPO and the Saturn section, such as during the Cassini mission, soliciting observations, digital images, and so forth from our ALPO colleagues worldwide. And that's continuing today, even though the Cassini mission ended back in 2017. Okay. People ask a lot of questions about what type of instrument do I need to be able to observe Saturn and regularly participate. We don't set some inflexible minimum, although we do recommend to start at least with a 4-inch refractor or perhaps a 6-inch Newtonian or catadioptric. Equatorial mount with slow motion controls and a clock drive certainly helps things out significantly. Color filters with known wavelength transmissions and a reliable ephemeris, the Astronomical Almanac, which is getting more difficult to get these days. WinJupos and WIMP, which was production by Jeff Beach, one of our colleagues in the ALPO. A digital imaging connected to a laptop for suitable software following image capture and subsequent processing. Okay. Saturn observations typically last 378 days between conjunctions. The main thing is to try to plan your observational programs well in advance and start observing as early in the apparition of Saturn and maintain some consistency with your observations. The key is to keep accurate observational records such as the UT date and time, the telescope, the location, magnifications, and any filters that are used. Use ALPO standard observing forms on a regular basis if you're making drawings and recording observations to get that data that's already available. Those forms are available on our website, or I can send them to you by regular mail. And we try to strive for simultaneous observations, and that means 2 or more observers viewing at the same time and the same date whenever possible. We have many instances where observers in our database, we can cross-reference to see that we have quite a number of those to confirm questionable phenomena. Okay. Okay, our observing programs, visual numerical relative intensity estimates, sort of like it's visual photometry using filters. Full disk drawings are still available. We have standard observing blanks that gives the proper orientation, as well as the tilt of the rings to facilitate drawing. We have a lot of observers that are still doing drawings of Saturn. Quite a number of observers now have moved over to doing digital imaging at multiple wavelengths. Some folks are still doing transit timings of notable atmospheric features. Visual estimates and measurements of belt and zone latitudes, that's described in my book. We talk more about that at some other, that's a different subject, but it's something that people are still doing. It's a method that Walter Haas developed years ago for doing visual latitude estimates. Visual detection of intensity minima in the rings, and to record the curious bicolored aspect that the ring assay and brightness asymmetries around the circumference of ring A, accurate timing of stellar occultations by Saturn, and recording of transits of satellites and their shadows across the globe at the point of edgewise ring presentations, and visual magnitude estimates of Saturn satellites is a process that people are doing as well. Okay, this is an example of the type of drawing form. You can see that the tilt of the rings is already shown. The blank makes it easier to facilitate drawing, and there's a space on the blank to record all the pertinent information such as the observer, location, type of instrument, magnifications, filters, and also to estimate the visual numerical relative intensity of the belts and zones on Saturn, as well as using ring components. Okay. All right, this is a typical illustration of the standard nomenclature for Saturn. There are two rotational systems on Saturn. System 1, 10 hours, 14 minutes, 13 seconds, the equatorial regions. And then for regions north or south of that, we've got a System 2, 10 hours, 38 minutes, and 21 seconds. Most of those features that you see labeled here, this is shows the northern hemisphere of Saturn at an approximate tilt of the rings at 20 degrees, which is a little bit greater than what we see right now, the 2122 apparition. It's about 18 degrees right now. Okay, the changing aspects of Saturn's rings over a period of 29.5 years, the revolution period. Saturn's rings can change from an edgewise presentation as occurred back in 2008 and 2009. Then when Saturn reached summer solstice, that was during the 2017 apparition, when the rings were tilted about 27 degrees to our line of sight. And then the next edgewise presentation of Saturn will occur in the 24-25 apparition. That does not look like that's going to be that favorable because of the location, but that's upcoming. There's one 30-34 after that. Okay, the current apparition, this is the opposition of information showing that conjunction occurred back on January 21st of this year. Opposition just occurred on August the 2nd, and conjunction will occur in February of next year. You can see that the opposition data shows that the equatorial diameter of Saturn is approximately 18.5 seconds. Global diameter of the globe is 16.3. Major axis of the rings, approximately 42 seconds of arc. Minor axis, 13 seconds of arc. And so you can see in some of the images I'm going to show you, the rings are starting to close up a little bit as we continue to move forward in time to the next edgewise presentation. Okay, here's some current observations of Saturn. This is before opposition that occurred on August 2nd. There are a number of features that have been seen by observers and imaged. There's a curious white streak that's been imaged in the equatorial belt. And we believe that this white streak in the higher resolution images are showing that these are possible white spots that are lined up across the disk and that seem to be merged to show what looks like a streak. Also, there's a white streak that's been observed and imaged in the North Equatorial Belt South component, as well as one in the North Equatorial Belt North component. Okay. More observations, more images of Saturn. You can see that some of the features I just talked about, again, the white streak that's fairly prominent, and it's a persistent feature that's been visible since the past apparition and seems to be a long-lived feature. And these, as I said, it appears that a lot of these features in that appear as a white streak are probably, or it looks like there are a host of spots that are lined up that have merged together. Okay, a few more observations of Saturn. Similar situation here where you can see a lot of the features on Saturn in multi-wavelength images, some in RGB, as well as people using IR filters, 685 nanometer IR filter for some of the images as well. Different wavelength channels as well, such as red, green, blue, to bring out some of the interesting features. Okay, some highlights. The rings, as I indicated, are tilted at approximately plus 20 degrees in this apparition, somewhat less than maximum ring tilt, but still permitting good views of Saturn's northern hemisphere and the north face of the rings. The Pro-Am effort that began back in 2004, when Cassini started imaging Saturn at close range. The project of Pro-Am cooperation is still going on, even though the mission ended back on September 15th of 2017. So as I mentioned earlier, when you were looking at the images, observers are reporting discrete features within the belts and zones, a recurring curious white streak that I just mentioned, imaged at in the equatorial belt at plus 5 degrees Saturnographic latitude, and plus white streaks in the NEB and NEBS detected at plus 14.5 and plus 16.0 Saturn graphic latitude, respectively. The same features, as I mentioned, were noted back in 2019 and 20 seem to be persistent as well. White spots just inside the North Polar region at 64 degrees the Saturn graphic latitude have appeared early this apparition. Apparition is some of the images that I've gotten at opposition show this same feature as expanding and hopefully spreading out in the NPR. The small white spot image in the equatorial zone south at -5 degrees Saturn graphic latitude has also been imaged and also re-imaged again this during opposition. And the EZN is quite prominent this apparition especially. And as I should mention, even though the southerly declination of Saturn is -18 degrees, observations are still arriving almost daily, even though the observing season progresses. It's been kind of low in the sky. Our guys in Australia have been very successful in getting good images of Saturn, despite the low declination. Okay, more about observing Saturn. My book, Saturn and How to Observe It, is available at places like Amazon, as well as as a monograph that is available on the ALPO website at no cost to observers. And that concludes my discussion.
Julius, Richard Schmuti. You've been recorder of Saturn for, I think, almost 50 years now. And it would be really great. I know that the BA did this way back when, is to get a year-by-year analysis of the mean intensities of the various belts and zones on Saturn. Do you have any intention of doing that?
Yes, we have that. I did quite a paper on that quite some time ago. Walter encouraged me to do that back years ago. And we've got a record of that. I can send that to you if you're interested to see what it shows. That's the relative numerical intensity estimates.
I'd like to see that because I've been doing photometry of Saturn. I'm trying to think. I think I got my first measurement in 1991 and have been getting it every year since then, except for 92. And so that would be interesting to look at that.
Yeah, Walter really stressed that. He said that visual photometry, just like estimating Saturnographic latitudes or Saturn-centric latitudes, which can be converted, interconverted, he felt that was a good enterprise that amateurs could participate in. And he did a lot of that. I've got some of the extensive records of the visual numerical relative intensity go back to his days.
Great, good, very good.
I believe he did a lot of that with Jupiter as well.
I would like to see that, yes, because I've got it from, early 90s, I think, but I'd like to see it from, like the 70s and 60s.
I will send you my graphs so you can see what they look like. They're quite interesting. There's a break in there where there were some observations that weren't done back maybe a year and a half apart from the others, but they're ongoing right now.
Good.
And I would like to do another study of that quite soon to publish something on that as well in our journal.
Good.
And you and I can coordinate on and see how it relates to the photometry stuff. Saturn's tough to do photometry.
Well, you've got the ring tilt, you've got the phase angle. Yeah, I know. And Tony Malama did a great job. I tried to do Saturn and got it published, but Tony did a better job. And yeah, you're right. Saturn's tough on photometry.
Yeah, especially with the Seeliger effect too. That kind of throws things off a little bit.
Oh yeah. That's you're right. Well, thank you. Very good talk, Julius.
Julius, one question I would like to add. I have seen quite a few images that somebody images the Maxwell division. Where they're located are you familiar with the Maxwell division?
Yes. Yes.
With
Ring D. In Ring D.
Okay. That's hard to see. I mean, I haven't. There's very few people that have imaged that.
Well, I've seen some of the images that Damien Peach has sent, and some of the guys in Africa as well as South Africa, as well as Trevor Barry down in Australia. I've tried to see if I was trying to see if I could detect that on their images, And right now, it's kind of inconclusive. No one's really called attention to it.
Right, yeah.
I believe our colleague Tom Dobbins called attention to that in a recent Sky and Telescope article.
Oh, visually, yeah.
Yes.
Okay.
All right, Julius, thank you very much. Good job.
Thank you. Enjoyed it.
Yeah. Next one up, we have Frank Maleo. He's going to give us a talk about his Mercury section. Frank's been interested in astronomy since the age of 11, when Apollo 11 went to the moon. And he used a Tasco 4.5-inch reflector through the 70s. In the 80s, he purchased a Celestron C8, and he still uses that today. He started doing astrophotography and joined the Astronomical Society of Long Island in 1982, then the AAVSO, then the IAPPP, and the ALPO in 1984. 1997, Frank joined the world of CCD imaging and got interested in planetary imaging. Frank's been very active in the ALPO, more than any other national organization since his career began. In 2001, he became the Mercury coordinator for the ALPO. That same year, Frank received the 2001 Walter Haas Award for the most outstanding contribution to planetary astronomy. In addition to his 8-inch telescope, he has a Meade 10-inch and several webcams for planetary imaging and a quantum hydrogen alpha 0.6 angstrom solar filter. All of these accessories have helped Frank further his planetary studies of our solar system. And with that.
All right, thank you, Tim. Let me share the screen.
Okay.
Anybody see it? Okay. Okay.
Did you want me to share? Did you want me to share it or you?
Let me see if I can. Let me see if I can share it.
Okay. Let me stop sharing then.
Yeah. Okay. Okay. Everybody see it?
You got it.
Okay. All right.
I just maximize it and you're good.
Okay. All right. Thank you, Tim. Welcome, everybody. It's really a pleasure to see you guys on the screen. Hopefully, you know, we cannot meet in person yet, so hopefully that will occur next year. So I just realized that it has been 20 years that I've been a Mercury coordinator, and it's hard to believe that. Since that time, I try to keep the session very active. I try to encourage many people to observe Mercury. And usually I collect the data, I collect observation, I analyze it, and report to the ALPO journal. I do basically every year writing an apparition report. Currently right now, I'm writing about 2020 apparition report. And there's a lot of things to observe Mercury, even though it sounds like a boring planet. But it's, if you know how to, if you plan well enough to observe Mercury, you get most of the details possible. Usually on the star party, I try to talk to many people, and when it comes to planetary observation, and I try to tell them, observe Mercury, and to say that, well, Mercury too close to the sun. They have a big telescope. They're afraid to point too close to the sun. It is always behind a tree, behind a house. It's always blurry, and so forth. Mercury had the reputation of being the most difficult planet to observe and to image, naturally because it's very, very low in the sky, because of the turbulent atmosphere. If you compare with Mars, Jupiter, and Saturn, those planets are very, very well observed. We have hundreds of images of them. And of course, Mercury is being neglected. Venus is so-so. So I've tried to encourage many people to observe Mercury, but if you know how to do it, you can be quite successful. So that's what I'm trying to do and encourage people, members, and all. So, so you might ask me, what's up with Mercury? Well, I'm here for the next 15, 20 minutes to show you what can be seen of Mercury. All right, so we have here a very simple image of having image of Saturn on Mercury. We have a camera, a simple technique to have a camera on a tripod, and if you have to images of Mercury right at sunset, and you have a very good chance to have image of Mercury. Like this image, for example, was taken last spring, and we have Venus here, and where is Mercury? Up here, if you see the little star here. So this was taken last May, taken right after sunset. So Mercury is always interesting to see when it is involved in planetary conjunction, either with Venus, Jupiter, or Saturn, or even the crescent moon. So it make more attraction to image of Mercury with the tripod and the camera on it. But here's a better image taken a few years ago, and you have the crescent moon involved, and you have Venus here, and you have Mercury up here. And this is a very rare triple conjunction here. But the funny thing about it is that look how far apart it is here. You have Mercury here, and you have a crescent moon here. So from here to there, it's about 70 degrees. If Venus is located right along the ecliptic, and the moon is very well south of the ecliptic, and you have Mercury well north of the ecliptic. And this is a very wide gap there. You call it conjunction, yes. As long as two bodies have the same right ascension. But it would be much nicer if we have all three of them in a very tight group. So that occurs very rarely if you have Mercury involved with planetary conjunction. Normally with Venus and Mercury, they have bypass, they have in conjunction many times though. So this is quite interesting. This is kind of rare picture because not only that, you have Mercury above Venus and the crescent moon. Always you see an image of Mercury always down the lower horizon while the other planetary above them. So we have Mercury above Venus and the crescent moon. So this is quite a unique shot here. Okay, telescopically, we have a new member just joined the ALPO earlier this year, that Gregory Shanos. I believe he's in the group right now. He got in touch with me, and it's very interesting imaging Mercury. And I gave him a few tips and all. He got a 10-inch meet like I do, and I recommended after surface software, which I believe is the best software to do planetary processing. And that's one of his first shot. Not bad for the shot. And this was taken last March 14. It was taken in the morning sky during the morning twilight from Longboat Key, Florida, right along the Gulf Coast, Gulf side. And he pretty happy with it. You got the face here, you got a possibility of a surface detail, which is it's hard to see at the moment, but this is a great start. Well, a week later, I have my share of image Mercury, and it was on March 20th, and the sky condition was okay. I was able to find Mercury in daylight, and finally, I got a decent shot here, and it's a possibility that you're able to see some of the ray craters, which I will explain that in a moment. Compared with the Messenger Window simulator, this is the day what Mercury supposed to look like the day I'm observing, and it's pretty much consistent with each other. And those two ray craters here, it's what you see here. All right, this is a little blurry and pretty much satisfying, but the next day it got a little better with the better seeing condition. Now you see a little clearly. You can actually see individual white spots here. Those are ray craters like you see here, and few clusters of ray craters on this portion here that condensed here. So not a bad photograph, but I always find Mercury with better seen in the morning sky than in the evening. Just to show you some examples here. Okay, we have our own Rick Hill. He also imaged in Mercury the same month, but they were taken in May 23rd. It was in the evening sky, right after sunset, and he was able to image the crescent face. Now, the funny thing about the crescent face, it's very, very hard to detect the detail. As you can see, though, the simulator messengers, and very little detail that can be seen. And Mercury is very, very hard to, regardless how sharp the image is, it's very hard to detect any detail on the surface when it's crescent. But all the way from half to gibbous to almost to full, because Mercury's surface exposes a lot more. And I will show you more in a moment. Another image taken by Gregory China. This is right after sunset in last May, and you can see it's one of the first images, and he not bad, and compare with the messenger simulator, and you can see a very, very similar. And unfortunately, this part of the surface is lack of ray craters, so not too many bright objects you will see here, except that there's a little one here, that Cupid crater, and you may have detected right along the limb here, and there's a few models surfaced here, and which may detect them on the messenger. Here's my images taken the same month. This is okay, but I always image in Mercury in the morning sky. That's when I find it seeing the best. But right after sunset, I hit a lot of turbulence. You know, that's very, very little successful I had with Mercury in the evening apparition. So you can see here's the fat crescent appearance, and even this one here. This was taken by Luigi Marone, one of the Italian astronomer. He take truly amazing image of Mercury, and of course it was taken with C14. And this is his image right here. And it's a possibility that he detected the Cupid crater, which compared with the messenger, and this is what Mercury will look like the day he imaged, and here it is right here. So he actually detected the ray crater Cupid, and there's a few subsided, very little subtle detail that you can see here. So that's parts of the surface here that lack of bright ray craters there, but there's only one that's the Cupid crater right here. Okay, now the next one is he created a 360-degree albedo map of Mercury, and here's the bright spot here, the ray craters, the one which they can actually help you to identify any features on the surface if you have a longitude and the latitude, so you can plate them and locate it, the feature by latitude and longitude. So, okay, now what we have here, we're going back to the comet. Well, is this a comet or Comet Mercury? It is Mercury sodium tail by an amateur astronomer. It actually looked like a comet. This image was taken by Andrea Alessandrini. He's an Italian amateur. He imaged Mercury on a tripod using a sodium filter. Now, the sodium filter isolated 589 nanometers, and that's with the most light emitted by sodium light emitted through the filter. And with very simple techniques, we put the camera on the tripod with a little bit of a telephoto lens, and you put the filter onto the camera, and with a little bit of time exposure, you can actually detect the sodium tail. It's amazing. Now, this opens the chapter of imaging Mercury by using a sodium filter in order to detect the sodium tail. Let me explain to you by the next image here. This image was taken by a messenger spacecraft and hooked up with a sodium filter. And what you see here, and we'll show you a short animation, and you can actually see the sodium tail at Mercury going around the sun. When it goes to further away from the sun, then it's dimmer, and then when it gets close to the sun, the tail gets longer. So in other words, that Mercury has an atmosphere now? No, not that we know of. Mercury has a sodium molecules is scattered around the surface, scattered around the global, and from the distance, if your eyes are sensitive enough to detect sodium light, it will form like a haze, and that's what you just saw right now. If you want to see it again, you can see as Mercury going around the sun, the tail gets longer and gets shorter as it moves away from the sun. So it's very interesting to see that. This is according to the length of the tail, and it was swung by the solar winds, and it formed like a comet. Very interesting. It depends how far away the Mercury from the sun. So the closest to the sun, the longer tail you would detect. When it's the furthest away, and the shorter tail you can detect. So that's a very interesting project now that it just coming up this year. And I planned to do the write-up for the journal. And the next image I want to show my good friend of mine, which he lives on Long Island. He just became an ALPO member, and he detected on May 13. And also he has a nearby crescent moon. And hit the image of Mercury here. But with a little bit of contrast and a little close-up here, he actually detects the tail again, right here. And if you look carefully, as you can see a little trail, because that's due to time exposure. So this is not tracking. This is just a simple camera on a tripod. And you just let it expose for a few seconds. And with the sodium filter, it's a possibility you can detect the sodium tail. Now, how soon can you detect that? Well, you don't want to do it when Mercury went too low in the sky, or when the sky is too bright. So it has to be like maybe in the mid-twilight, and it has to be in a favorable apparition, during, either in the morning or the evening sky. If you plan well enough to try to detect the sodium tail, you can do that. The sodium filter, 589 nanometer, it's if I believe, is sold by Edmund Optics. They sell that kind of filter, an inch and a quarter. But you can do with a short refractor. You don't need a large telescope to do this. Just a camera with a telephoto lens and on a tripod. You don't need to be tracked. Just a short exposure. And you can it's a possibility you can able. Now, I haven't tried that yet, but I will try to get the filter, and I like to experiment myself. This is like open up the new chapter of imaging of Mercury. This is very similar to when you detect Venus dark side with the 1 micron filter. This is almost the same thing as this. And now you can experiment with it, and you can see how long the tail is according to how far away Mercury to the sun, whether it's closer to perihelion or an aphelion. So that's the thing. I'm planning to do the write-up on that, so hopefully we'll get it done soon. Okay, now, as the world turns, this is the global map of Mercury by the Messenger spacecraft. Okay, now I want you to look very carefully. If at Mercury's turn, you can able to see white ray craters, how bright they are. This here, over there, and one here, the bright one here, there. So that's pretty much easily visible. The ray craters are the most visible features that you can see on Mercury. Now, last November, I did extensive work on Mercury. That's probably the best work I ever done. And what you're going to see here, I have imaged Mercury 10 days during the favorable morning apparition last November. And I planned this well in advance because there's a few reasons. Because at that time, the visible Mercury, the surface visible is the most interesting ray craters would be facing toward us. And also during the month of November, it's seasonal mild compared to the winter months, and also Venus was nearby. So if you get Venus in the daytime, and if you know what Mercury is by using the setting circles, then you can able to set up the coordination and you find out pointing where Mercury should be at that part of the sky. So so everything fell in one place, and it became very successful. It's the best work I've ever done. Of course, I did a write-up on this, and hopefully will be published in the next issue or the winter issue or whatever. And this is to show you how well Mercury could be seen if you plan well in advance. This is some of the examples here. This is November 7th, 8th, 14, 16, 18. So you can able to see, if you look carefully, you can see all these white ray craters, the white dots. That's the most prominent features you can see. And these are the messenger window simulators. So this is you can compare with my image, and you can actually see what's real or what's not real. So it's pretty consistent with the messenger image. And of course, continue the next day. The next slide, you can continue to image Mercury even on 19th, the 20th, 21st, the 27th, and 29th. The whole month of November took 10 images. Luckily, the weather was great. I was lucky on that. And so that's why I have almost every other day. And you can actually see the ray craters moving across the disk. And even when it's full, this is actually the first time I imaged Mercury nearly a full face. As you get full face, then you get closer to the sun. So so that have to be very careful about it, because the telescope was in the shade. It was blocked by the roof of the house. So I was able to observe Mercury safely. But I do have, like I said, I did a write-up on that and explain every little detail how observations were made. So, okay, here's the map here to show you what I had imaged. These are the features, visible features that you see in the image. I have a list here. I can able to identify what I image here. His number one is the ray craters here. Number two is not a ray crater, but it's a dark crater. It's the double rim dark crater. It's very flat and has a very dark floor. So it gives enough contrast to be seen. And these are number three. It's not a ray crater, but it's a very bright area. I think it's called Amperici Panidia. Okay, and then you have 4, 7. These are all detected in my image. And again, this is Cuba number 10. It's the brightest ray craters, I think, in the entire surface of Mercury. And you're able to see, and pointed out, you can see right here. Right here. And this two here, and another crater right here, which you see, I think it's better here, right here, this two here. And you can see this image right here. And even even the smallest one, you can able to detect it, like this one here, and that one number 5 and 6. And you can able to see 5 and 6 here. That's the better image here, right here, there. Here. So this helps you to identify, the feature. Number 11 here, Getty's. There's a possibility that this may be the ray crater that I imaged. But the funny thing about it, it looks so small compared to the brightest one. It depends on the solar angle. Certain time as you view on the Mercury surface, it depends on the solar angle how bright the ray crater should be compared to the center, or when it's close to the limb. It changes as the phase change, according to what's seen from Earth. So sometimes it's brighter and sometimes it's dimmer. Now, the next image I want to show you, that I made a short animation of 2 images. Take November 7th and 8th, and you can able to see that a very slight rotate from left to right. And you see some of the details here. But wait, the next one is even better, because I have about 6 images here from the 14th to 21st. So this is basically almost every day from the 14th to the 21st with 6 images. And you can able to see the face changes, and also you can see that the ray crater is moving across the disk. Now, does that mean you actually see the rotation? No, it's not a rotation. It's the orbital motion as you see as you're going around the sun. It changes as the face is moving around the sun. It's not an actual rotation. Mercury takes 88 days to go around the sun, and Mercury rotation itself takes about 59 days. So I explained that more details in my upcoming paper, and what you see that you're able to see like one ray crater, and you can see the terminator advances, and at the same time the ray crater is moving consistently with the terminator. But if you look carefully, you can actually see the ray crater actually moving faster than the terminator advancement. Well, that's kind of hard to explain. It depends how close Mercury to the sun. When Mercury is closer to the sun, it moves faster, and when Mercury is furthest away from the sun, it moves slower. But the rotation stays the same. So actually, that when it's close to the sun, Mercury rotated a little bit faster. But when it's the furthest away, the terminator moving a little slower, and the rotation of the surface feature moving a little faster, because Mercury's moving slower when it's furthest away from the sun. So it's a little complicated, but I explained that detail more fully in my next upcoming paper. Now, this one here, 2 images 2 days apart, you can actually see almost a full face. You can actually move from left to right, and look how many ray craters you can see. I don't know, it's hard to count. I see 1, 2, 3, 4, 5, 6, and they all move together. So that's what I'm trying to say, that when the face is about half gibbous or closer to full moon, there's Mercury exposed to much of the surface, and you can see a lot more detail, but the condition had to be just right. Got to be very well focused. You got to be very well tracking. Don't forget Mercury, it's small, 5 odd seconds, 5.5 to 6.2 odd seconds. So everything has to be right. And secondly, I have used the Bay Batter 610 nanometer long pass filter. So it's a red filter. So that helped to increase the contrast against the background. It also increased the contrast on the surface itself. So that's why the ray craters appear much brighter. And you can actually see that the most prominent features visible are the ray craters on Mercury. So, okay, now the final message, the ALPO Mercury session will continue to collect the observation. How many adjusted ray craters worldwide can be seen in amateur telescope? What I just showed, that's just one part of the surface. And one part of the surface, I already detect about 6 to 7 ray craters. So imagine other part of the surface, and I detected from last March, the 3 ray craters I have in a line from north to south. So that, in addition to that, and also what are the brightest ray craters? Well, I just show you that so far the 2 brightest ray craters are Allerton and Debussy, the 2 craters there. But the Cupid crater might be the brightest of the whole surface of Mercury. It depends on the solar angle seen from Earth. So I just explained that. And sometimes it's dimmer in the center, or it could be brighter in the center, or dimming on the edge when it's close to the terminator or to the limb. It depends. So my images show the animation. It's a very good way of saying to catch any details. It's more eye-catching a way to follow the detail. But they're very subtle or very faint. But you're processing, and you have to be very careful. And that's probably the best work I ever did. So, okay. So still more work needs to be done. I mean, to find out all about ray craters. Then I haven't gone anywhere for the past couple of years. So, keep observing Mercury. And if I ever go to the travel agency, and I would love to go somewhere, and they ask me about the planet Mercury, I will be the first to go. Yeah. So that's it, folks, and I hope you enjoy your presentation.
Frank, very good talk. One of the things you could start thinking about doing, you've got some great images of the raid craters. Pick one crater up, let's say Kuiper. Measure how bright it is. You can actually do that using disk integrated photometry and see how its brightness changes as the phase changes.
Yes. Well, I mean, that's just only one window that I just showed, one animation showed. But even if the other years, whether it would be the same as this year, or maybe if I do it again next year, and compare with this one and see if there's any changes. So that's a possibility. Yes. To work with the filters, something like that, and if you have the plane well in advance, it could be done. Yes.
Yeah, I choose the V filter because Tony Malama has published a really good photometric model of Mercury, and that would be the filter I choose, is the V filter, and that's useful work. I mean, I don't think that has been done before.
No, see, my work I've done with the red filter. I haven't done anything with the blue filter. It's a lot more work involved, and this thing had to be very quickly. So you got to plan this well in advance. Observing Mercury, you have a very short window. It's just like, okay, let me wait an hour and see this.
I know.
It had to be done quickly, if possible.
You're right.
Not like the other planets, like Mars, Jupiter, and Saturn. They're visible in the midnight sky, and you have all the time in the world to do any kind of experiment. But Mercury, very, very quickly.
Raid lunar craters are taken to be an indication, evidence of youth. If the older lunar craters don't have rays, it's said because of the solar wind eroding material. If there are raid craters on Mercury, does that mean there's relatively recent bombardment? Or is there some other reason?
Well, all right, like you see on the moon, you see all the great craters on the moon, like Copernicus, Tycho, Kepler. You see the rays nearly stretched across the moon. Okay, now compare with Mercury, you see those ray craters are very, very short and more intense because Mercury has a very, very strong gravity than compared to the moon. That's why the great craters are so short or small, and they're very intense, and that's why they're very bright. Is that because of the solar winds? Well, I really don't know. I don't think I have the answer to that, but the impact has something to do with Mercury has a stronger gravity than the moon does. The moons have a weaker gravity, so when there's impact on the moon, it just all the elements, all the elements, it just shoots across the face of the moon, and that's the real difference. Because of course Mercury has we don't know if there's an asteroid, another asteroid belt between the sun and Mercury, but it hasn't been proven yet. But it's been bombarded a lot during the early days, so you can see those ray craters now. Whether recently, we don't know. I mean, there's no weather on Mercury, so there's no erosion, nothing being raised. But the only thing is probably the solar winds be able to maybe change a little bit the intensity. So I don't have the answer to that, though. That's what I think, because there's no erosion on Mercury. Mercury has no atmosphere, so it probably been like that for many, many years. So.
Thanks for showing us those superb observations. It was remarkable that people are now able to detect Mercury's sodium tail. And I wondered, do you know whether anyone has tried that on Io as a telescopic object? Because, of course, Io has a sodium cloud as well.
The sodium filter. Well, anybody on your side there, or what?
No, I'm asking whether anyone has tried detecting Io's sodium cloud,
No,
as
I don't
people are
think-
now detecting Mercury's sodium tail.
No, I don't think so. No.
Hmm.
Yeah. Only the sodium. I don't know about the ion. I don't know.
Yeah, but Io has a sodium tail, a sodium cloud, as well as a plasma cloud.
Oh, okay. I don't know, but I'm doing the research then. Like I said, I'm doing the write-up. I have enough observation. I'm going to try to do one myself. And the sodium tells that it's even the moon, which I believe that has some sodium molecule. And I don't know if it can be seen, but I read about it. But Mercury it's close to the sun, and we have with no as Mercury may have an exosphere, and the molecule, the sodium molecule, is so far apart, it's not even considered an atmosphere. But like I said, if our eyes are sent enough to see the solar light, it was surrounded by the gas, by a shell of gas, and you see the solar wind from the sun. The intensity, the sunlight rays. You can see the solar winds. So yeah, so I'm planning to do the write-up again. Yeah.
Great. All right, Frank, thanks very much. That was very interesting and entertaining. Enjoyed that. All right, we're running a little bit behind today, but I need to take a 20-minute break. So we will break here and come back in 20 minutes. So that's about 12:40, we'll call it, okay? 12:40 Pacific time. You can do the math for your time zone. So we will see you all in about 20 minutes with Richard's next talk. All right, I'm back. Wait for a few more people to join us. They trickle in. Okay, I see, Richard, you're still eating. If you want to start your presentation, we can.
May I butt in for a second, Tim?
Sure, Ken.
I respectfully ask the rest of the speakers to please hold to their 15-minute time. Richard, Carl, and Scott. I know it was scheduled to have a 2-hour break between the end of the sessions and then the beginning of the Damien speech talk, but you know, that's getting eaten away, and I've got errands to run, and some of you may also. So please, Richard, please stick to your 15 minutes.
All right, Richard, you ready?
I think Richard needs to unmute.
Okay. Oh, okay. I'm ready. Okay. I'm going to talk about one recent development on Jupiter. Then I want to update you on some brightness measurements I've made. And so in the next slide, just two things I'm going to talk about. And I'm going to talk about, first off, I'm going to talk about the North Equatorial Belt. It has done something weird this year, strange. And then I want to talk a little bit about my J&H filter brightness measurements of Jupiter. This is a continuation of the work that I started back in 2014. So on the next slide, the North Equatorial Belt. How many people have seen Jupiter through the telescope? Okay. The North Equatorial Belt is one of the two bright stripes you see on Jupiter. It's the northern of the two. You've got the northern and you got the southern stripe. A lot of people think they're rings, but they're really cloud belts. The latitude measurements of this belt has been made for over a century, and these have been summarized in John Rogers' classic book, The Giant Planet Jupiter, which I'm showing to you right now. Now, the south edge of the North Equatorial Belt is known as the NEBS. The north edge of the North Equatorial Belt is NEB, of course, NEB stands for North Equatorial Belt. So in the next slide summarizes a graph. Now, what I did is I measured the latitude of the north edge of this belt, that's the orange, and the south edge of the North Equatorial Belt, that's the blue. And you'll notice not much change in the southern edge. That's the edge bordering the equatorial zone. But the north edge changes a lot. You can see the changes, and it changes by, probably up to 7 or 8 degrees. However, You might want to move this over. This is really unusual. This last point here, that corresponds to this month, August of 2021. Now, another way to plot this data is to look at the width of the North Equatorial Belt. That's just the latitude of the northern portion minus the latitude of the southern portion. That's known as the width. And that's shown in the next slide. And you can see the width has fluctuated from about 8 or so degrees up to about 16 degrees. There was a little drop here in about the year 2013, down to about 5 degrees or so. But then look what happened here in August of 2021. It is really narrow, something like 3.3 degrees. Now, how unusual is this? Did a little bit of statistical analysis, and basically I calculated the standard deviation of, probably about 22 or so years of data. And this is what I came up with for that time increment in the next slide. Basically what we have is the mean latitude, that's how high up the belt is. This southern edge has got a mean latitude of about 7.3 degrees north, with a standard deviation of almost 2/3 of a degree. The northern edge, the mean is around 18.8 degrees north latitude, and the standard deviation is 1.94. Now again, this is only data from 1995 up to 2017. I didn't look at the data before 1995. That's summarized in John Rogers' book. But I believe, as I recall, it's pretty close to these values. To give you an idea, in the next slide, we look at the standard deviation. That's very important. That tells us how clustered the data is. Now, the northern edge of the NEB, the position is 4.4 standard deviations lower than the mean. This is roughly 1 in 10,000 chances of that happening. So statistically, this is a very unusual location for the northern edge of this belt. Something like getting snow on April 15th to April 30th here in Atlanta. I mean, it could happen, but it's so unusual that we really don't talk about it. Now, the width of this belt was almost 4 standard deviations lower than the mean. And again, this would be, again, about 1 chance in 10,000. So extremely low. In fact, my statistics book doesn't even talk about 4 standard deviations. It'll go up to 3 standard deviations. I had to go to this internet site to find out, well, how unusual is it for something to be 4 standard deviations away? So again, about 1 in 10,000. So again, the North Equatorial Belt is unusually narrow. So if you get a chance, you need to get your telescope out and look at this, because this is probably a once in a lifetime event. All right. So that is a little bit about the North Equatorial Belt. Of course, John Rogers talked to you about a lot of the interesting events on Jupiter. So on the next slide, I want to briefly talk about photometry. Now, of course, I talked about it yesterday. Basically, we measure the brightness of Jupiter in a comparison star. We use the comparison star as the standard, compute the brightness, and then normalize the brightness for changing distances. Now, I have in the next slide, this is a picture of my equipment. It's just a tripod, clock-driven tripod. I do need power for the photometer. The clock drive operates on batteries. I've got my telescope here, my SSP photometer here, and then a light shield over here. And I'm pretty much good to go. I just need AC power. Now, I have, during the last few years, sort of moved over to the infrared, largely because Tony Malama and myself have written up good reviews on the V filter brightness of the brighter planets, and they're in the professional journal Icarus. So the near infrared was a logical choice for me to switch to. All right, now, basically, the next slide just summarizes what I just said, but in word form. I use an SSP4 single channel photometer manufactured by Optech. The two filters have wavelength sensitivities that are beyond that of commercially available CCD cameras. So you can't do this work with a normal CCD camera. You have to get a specialized camera, and of course they are not mass produced, which means they're going to cost you money. I know there's one couple over in the United Kingdom, I believe their last name is Ackerman, has done some near infrared imaging. So Richard McKim talks about them briefly. I believe it's in the 2012 Mars report. I may be an apparition off on that. So little work has been done with these filters for the planets. I know the AAVSO is using them for variable stars, but very little work has been done for planets. So in the next slide, again, some nomenclature. The normalized magnitude, I just write it as x1 comma alpha, where x is the filter. In my case, it's either the J or the H filter. And again, you have to correct for changing distances because the distance between Jupiter and the Earth and Jupiter and the Sun all impact how bright it's going to be. And I have found out that there's almost no change with the changing phase angle of Jupiter. Again, Jupiter's phase angle only goes up to about 12 degrees. Now for Mars, it's a different story entirely. Mars's brightness changes by 50% or so with phase angle. And of course, the phase angle is just the angle between the Earth and the Sun measured from the target, which is Jupiter in this case. Now, I've been measuring the brightness of Jupiter in these two filters since around April of 2014. So in the next slide, I wanted to show you my apparitional mean values, where the blue dots, and again, I don't know how to make these dots bigger. The blue dots correspond to the J1 alpha values. The orange dots are the H1 alpha values. And again, you can see the H values are pretty consistent. Right now, we're near equinox for Jupiter. We were also at equinox around 2015. So again, I don't see too much of a difference there. I don't see too much of a seasonal change here, as this point and this point are about the same as these five here. And then for the J filter, I don't know. There's a little more scatter for the J filter. But anyway, my data does not indicate there's a seasonal change for Jupiter. However, the tilt of its axis is only about 3 to 4 degrees, so that probably would not be too surprising. So in the next slide, I'm just summarizing my mean results. We got the filter and then the mean normalized magnitude. This is where Jupiter's distance is 1 AU from the Earth and the Sun. Of course, that's unrealistic, but at least it's a good way to compare values from one year to the next. And one interesting thing is Jupiter is dimmer in the longer wavelength light than in the shorter wavelength one, which is unusual, but it is what it is. All right, so just wrap up with some conclusions in the last slide. Jupiter's NEB is unusually thin. In fact, probably once in a lifetime thin. Again, one chance in 10,000. I mean, 10,000 months is what? Something like 800 years. So this is very, very unusual. And then, of course, Jupiter's J and H filter values have some scatter. This scatter actually is to be expected, though. Actually, it's a little lower than what they say of 0.05 magnitudes, and but does not show any definite seasonal change. And I do want to thank Gordon State College for providing me funding to purchase the SSP4 photometer, and for those people who have carried out images of Jupiter. And I apologize. I meant to include 3 images of Jupiter. I just realized I forgot about that. But anyway, my apologies on that. I wanted to include one of your images, Rick, but I don't know, it just slipped my mind. So anyway, I'm open for questions.
I have a question,
Yeah.
Richard.
Yes.
In the brightness measurements you made, it looked to me as though there was a subtle increase in brightness in the last year. And I wondered whether you think that's due to the narrowing of the North Equatorial Belt.
Interesting point, Roger. That's a very interesting point. And there's a good chance that it is. My only concern is I don't have images in those wavelengths of light. Now, I suppose I could do an internet search because maybe a professional observatory has done that. Maybe I can get this couple over in the UK to take an image too. That might be a good idea. I mean, I may want to contact Richard McKim and see if the NEB is very narrow in the, so for example, the H filter. That's a good suggestion, Roger. And I think that you could be right.
Richard,
yes.
I wanted to do those filters that you're using include any absorption by methane or any other gases? I can't remember the exact absorption spectrum along that region.
I am pretty sure they do. They are standard filters. The Mauna Kea, they were calibrated at Mauna Kea over in Hawaii, and I'm sure there are some absorption. I mean, I would be surprised if there weren't. And that would be, again, if I can get a spectrum of Jupiter, that could be something that could give me some clues there.
And if I could ask one more as well, do you still do any photometry in other color filters or only in the near infrared? Because I was wondering whether you're able to monitor changes in color as well as any changes in overall brightness.
Occasionally I do. I'm sort of keeping the B and the V work to Uranus and Neptune. One problem is my photometer. I just purchased another visual wavelength photometer 3 years ago, and I got about 1 year's worth of good work out of it. And then in early 20, for some reason, I don't know what happened, but it's giving me spurious results. And I think something happened to the photometer, but of course we've had to deal with COVID the last year and a half, and I need to call Optech and see if I can get that fixed, because I'd like to do a little bit more work in Jupiter. Yeah, color, B and V work.
Thanks, Richard.
Good suggestion, Chuck.
Thank you, Richard.
You're welcome.
Tim, you're muted.
Oh, sorry about that. I'm sitting there talking to myself. All right. Thanks, Richard, for that. Now that brings back Carl, who's going to give us an interesting talk about planetary objects on coins and metals.
Yeah, so something a little different here. So planetary numismatics. Numismatics is just another way of saying the study of coins and metals. Just a question to the group. Most of what I'm going to show is stuff that was minted back in ancient civilizations, Greek, mostly Roman times. And of course, in order for an astronomical or planetary phenomenon to be put on a coin, it must have been impressive to the powers that be. Does anyone have any suggestions, ideas as to what sort of things you think would have made it onto a coin? Obviously, I'm right here, I'm showing a whole bunch of comets, so we know comets made it on.
A comet, and I think, correct me if I'm mistaken, Carl, but didn't a comet appear about the time Julius Caesar was assassinated?
Yes, in fact, I have a whole slide on that, but that is the upper middle coin there.
Okay.
Is a coin minted
conjunctions. I'm sorry, conjunctions,
Yep.
appearances of the moon, planets, stars. These were used by the mint to note the time. Ancient coins were the newspapers of their era. So if the emperor did something significant, they'd like to have a timestamp on that. And the astronomical event could have served that purpose, especially in ancient times and in Rome. As you move forward, there were other reasons, just mint control marks. Sometimes it's not easy to know whether the astronomical symbols are arbitrary or meaningful, but by all means, just about anything that happened in the sky that was visible could end up on an ancient coin.
Correct. Now, this is not going to be exhaustive. I'm not going to go into every single instance. I'm just kind of picking things that I found kind of cool and I thought the group would like. We know nowadays, like the U.S. Mint, they mint commemorative series. Like, you know, we had the 50 state quarters, we had all the national park quarters, we had the president dollars, we had the first lady gold pieces that have all been minted. Well, it turns out the Romans sometimes did something similar. These were all coins minted in Alexandria. This is in Roman Egypt. Egypt always had kind of a different monetary system than the rest of the countries around it. The Romans kept that. Coins were allowed to leave Egypt. New coins were not allowed to come into Egypt. But these drachms, minted during the reign of Antoninus Pius, so you're talking middle 2nd century, middle 100s AD, actually showed a zodiac. You've got a zodiacal wheel here with all the zodiac going around the center, but also you've got each of the individual constellations with the deity or planet that was considered the controller of that constellation. Like you had Mars in Aries, the Sun in Leo, you got Jupiter in Pisces. Where's the moon? Moon's over here in Cancer. So it's interesting, even then they kind of had commemorative series. As was mentioned before, moons and conjunctions were very considered important and were often put on coins. Often, if you do see the moon, you see the crescent moon. Sort of makes sense. I mean, it's hard to kind of draw a full moon and have people know that it's actually a moon rather than just a circle or a shield or something like that. But the crescent moon, even now, when people draw the moon or put the moon in, you know, cartoons or in movies, it's almost always a crescent. The crescent seems to be the most portrayed phase of the moon. And you'll often see the moon involved with either a single star, sometimes up to 9 or 10 stars, though quite often 7 seems to be a nice number that you constantly see with your coins there. And so what you're probably seeing in this case could be as simple as, you know, the most visually impressive lunar conjunction is the moon with Venus. But also you have 7 stars, which makes you wonder, could this be the moon with, say, the Pleiades, which is also a visually very impressive conjunction that you would see. The thing that really kicked off this talk was there was an auction selling a whole bunch of these coins, and these are what are called Greek imperial coins. They were minted in the Greek-speaking part of the Roman Empire, which is really the eastern part. And in fact, all of these coins come from what is now modern-day Bulgaria, maybe the European part of Turkey. And there was about 200 coins for sale, and then this coin showed up. That to me looks like, of all the coins I've seen, shows Earthshine. I mean, it really does look like you have what's kind of a crescent part of the moon. You got your star here, and then it just does look like there's Earthshine there, which is kind of interesting because usually when you do see a crescent moon, the Earthshine is very obvious, yet it's rare that you actually see Earthshine portrayed in modern media, and almost never seems to be portrayed in, you can think of coins as ancient media. Yet here looks like an example of Earthshine. Now, when I mentioned that there are quite often 7 stars shown, and the question is that the Pleiades or is it something else? Well, for the ancients, there were 7 planets. There was the Sun, Moon, Mercury, Venus, Mars, Jupiter, Saturn. Earth didn't count, wasn't considered a planet. Sun and Moon were moving just like everything else were considered planets. So it's very possible that what you're seeing here, though it's interesting because the moon's there too, and the moon would be counted among these 7, but it could just be the moon also represents, say, the heavens, and then you have the 7 moving bodies that are within the heavens. Now, there is an interesting coin. This is Roman Republic, so it's around 109, 108 BC, that Marshall Faintich, who actually literally wrote the book on astronomical symbols on ancient and medieval coins, suggests that what we see here, crescent moon with 3 stars and then a star down here, might actually be this conjunction that was seen in the evening sky in June of 109 BC, where you have Venus down low, you have Mars and Jupiter, and I believe that is Regulus there. There's kind of the tail of Leo with the moon. So for whatever reason, this conjunction was considered impressive enough that it was commemorated on this coin. Now, a coin that I really find interesting, and a lot of people have been discussing for years, is this coin that happened later in the Roman Empire. This is Emperor Julian around 360s AD. And it's very odd because you just do not see this reverse symbolism, this iconography on any other Roman coin, where you've got a bull and then two stars. And one star is always between the horns of the bull. The other star is always over the back. Quite often the stars are equal in size, but sometimes the star that's within the horns is smaller than the other star, and it's never the other way around. So one suggestion was this was the Apis bull. The Apis bull was Egyptian. It was a bull that represented Osiris, and Serapis, which was kind of amalgamation of Osiris with other gods. And this bull would be found among all the bulls. It would have a certain distinctive color pattern, and it would be venerated. And then when it passed away, they would find another, they would search until they found another bull with a similar color pattern. And that bull was, a bull like that was discovered around that time frame. But this also happens every 20 years. So why all of a sudden this time? Well, it's possible because at this point in the Roman Empire, the empire is well on its way to becoming a Christian empire. This is after Constantine. So Christianity is no longer being persecuted or simply just somewhat tolerated. It is now considered one of the religions of the empire. In about 10, 20 years after the reign of Julian, Christianity will actually be declared the official religion of the empire. And then you'll actually see the pagan practices start to be persecuted. Julian, for whatever reason, kind of was a little bit of a throwback in that instead of being Christian like the rest of his family, and he's part of this Constantinian dynasty, he was very pagan. And so there was, maybe that's why he commemorated this Apis bull on there. It's possible the bull just represents the emperor himself, the strength of the emperor. In fact, the reverse legend here, Securitas Repub, means security of the republic or security of the empire. The emperor was really into various religions like Mithricism. He was supposedly really into sacrificing bulls, to the point where there actually are texts where certain, like the people of Antioch, were making fun of him for all the bulls that he was slaughtering during his religious ceremonies. And even in particular, making fun of this coin with respect to that. It's possible this is Taurus. This represents the emperor's birth sign, or just a constellation or zodiacal sign that was important to him, where maybe these two stars represent the Hyades and the Pleiades. That's one possibility. Or some people have suggested that this represents a planetary conjunction which occurred in Taurus around 360 AD, where Mars and Jupiter actually got close enough together in the evening sky that they almost merged into one. Visually not very impressive. Venus would be much brighter than Mars. And as we saw with the Jupiter-Saturn conjunction, or at least this was my experience, it was great until you got within a few days of the conjunction, and then Jupiter kind of just swamped Saturn, and it was hard to tell that there were two objects there. Moving on, transits and solar conjunctions. So now we've left the Roman times and we moved on to basically medieval times. We're talking the 12th century here, so late 1100s. And there was an Islamic dynasty located roughly northern Iraq. And they actually minted a very impressive and cool series of coins. One of the things they like to do is they would take the iconography of much older coins, whether they were Greek, Roman, Byzantine, and put it on here. Like here, you actually see this sort of, the style of the two figures here is similar to what the Byzantine or Eastern Roman coins would look like with the emperors. And here, the style here is very similar to what you saw on late Roman coins, like for example, here on the Julian coin. At this point in time, they were really into astrology and were really good at predicting conjunctions and astrological events. The coin up here has been suggested to represent, even though you'll notice it says when Jupiter passed, basically a conjunction where Jupiter passes in front of the sun. We of course know that's impossible, but it does turn out in 1189, the sun occulted Jupiter. not observable, of course, in 1189, but it was something you could predict. And the belief is that these two represent the sun and Jupiter. The coin down here actually may represent a transit of Mercury across the sun on April 21st, 1181. Probably not observable without optical aid. I'm not even sure a Venus transit would be observable without optical aid, even though large sunspots can be observed, but was definitely predictable. And the thinking here is that you've got Mercury passing in front of the sun. And as we mentioned before at the beginning, comets are all over coins. The most famous being, of course, Caesar's comet of 44 BC. Julius Caesar was assassinated by a group of senators. A little while later, there were commemorative games thrown in his honor, his funerary games, mostly thrown by Gaius Octavius, who would later become Emperor Augustus, who was Caesar's adopted son. And during the time of those games, there was a brilliant comet seen in the sky. And a lot of people took that comet as a sign of Caesar's apotheosis. I might be pronouncing that wrong. Basically, his soul ascending into heaven and Caesar becoming a god. And so, of course, it was great propaganda for the adopted son of Caesar to start claiming that he was divi fi, son of a god. So the coin of the comet of Caesar shows up quite often on coins of Augustus. A lot of other comets, especially bright comets, have made it onto coins. We've got the comet of 1618 from a coin in Germany. Comet of 1744, again from Germany. You see Hamburg really likes putting comets on their coins. This is a comet of 1680. And this coin here is kind of interesting because there was a coin minted. It looked like this on the reverse of the comet of 1578. And when the comet of 1881 came around, they kind of made a commemorative piece commemorating not only the 1881 comet, but also calling back to the 1578 comet. And it is interesting, some of the text on here, like for the comet of 1680, the star threatens evil, but trust in God and he will make it well. Or here, for the 1881, 1578 comet, the star of offended divinity. And even 1744, it was a line from Romans, who has known the mind of the Lord? So these are all either showing comets, but also portraying comets as being kind of maleficent and evil. And this is a cool gold piece minted by Pope Leo X from the Papal States there in Rome, which actually shows the three wise men. Instead of following a star, it really looks like they're following a comet. And remember, there's a reason why the Giotto mission to Halley was called Giotto. It's because in one of Giotto's paintings, he had as the Star of Bethlehem not being a star, but actually being a comet. And moving on in time, I found this to be a really interesting piece. This was a British tin medal minted in 1810. It shows the zodiac, it shows the orbit of the Earth, where the solstice is and the equinox. And on the back, it shows kind of the orbits of the planets, or at least what was known in 1810. And when you zoom in, you see Mercury, Venus, Earth, Mars, the four asteroids that were known, Ceres, Pallas, Juno, Vesta, Jupiter, Saturn, and then Herschel. Uranus wasn't, after William Herschel discovered Uranus, originally he named it after King George. That, of course, didn't go over well to pretty much anybody outside the British Empire. And eventually it would be named Uranus, but there was a while where it was just simply called Herschel, even though you'll know Herschel is actually spelled wrong here. It's missing a C there in the middle. And it even has the old astrological symbol for Uranus, which was an H, because the name was Herschel. And it really wouldn't be, I think, till 1850 that everyone agreed that Uranus was the name of Uranus. And here's another nice piece for all you Saturn lovers. And this actually was minted by Louis XIV. Well, it was minted during the reign of Louis XIV in France. And Cassini, even though he was originally of Italian descent, worked in France and discovered, Titan was discovered by Huygens, but then Cassini discovered, I think, the next 4 Saturnian satellites. So you actually have those discoveries on here as well as Titan. And you can actually see, it's hard to see, but you'll see the numbers 1, 2, 3, 4 up to 16. So it's a 16-day orbital period for Titan. And then this is Iapetus, going all the way to 80 days, and Iapetus has around a 79.5-day orbital period. And then for my last slide, the most recent stuff, these were actually medals that were awarded for the discovery of comets. The most famous being the gold comet discovery medals that Frederick VI, King of Denmark, used to award in the middle of the 1800s. This medal in particular was awarded to Maria Mitchell, who was the first American to discover a comet back, I think it was in the 1840s. And then the Astronomical Society of the Pacific for a long time, between 1890 and 1950, would award medals to every discoverer of a comet. These weren't gold or silver, but you would get a medal. And this particular one was to John Grigg of New Zealand. And this was commemorating his discovery of comet Grigg-Mellish in 1907. That is the end. And hopefully I got us a little bit closer to being back on time.
Very good. And how many of these coins do you own?
I own, this is the Grigg-Mellish discovery coin.
Oh yeah.
There. Found that. This is the only, in my 30 years of looking for coins, I think I had it upside down there. This was the only comet discovery medal I've ever seen offered. And I've done searches and it's the only one I found. So I made sure to grab this one. It didn't set me back too much. And I was finally able to purchase, well, I should say I was finally able to. I finally decided to part with enough money to purchase. I don't know if you can see it. This is the bull coin from Julian. Yeah.
Wow.
I have put down bids forever on that Caesar coin, and those coins go for $1,000 or more a pop now. So it's, yeah.
Hey, Carl, who sells these coins? I mean, any kind of coin collector or what?
Yeah, I mean, for ancient coins,
I mean, are they worth a lot of money or something or what?
they can be. Yes, they definitely can be. Some of those coins I showed on there go easily for a couple $1,000s. That probably gold coin from the Pope probably goes for about $10,000.
Wow.
There's various auction houses that specialize in
the sizes, right? The one that you showed, it's like bigger than the silver dollar or bigger than that.
Yeah, this is about quarter size.
Quarter size.
Usually they're, a lot of the coins are dime size. The metals can be larger. And this is a pretty good chunk. It's like silver dollar size. You can get really large metals. They're pretty rare.
Are they heavy or what?
This one's got some heft to it. Yeah, but in general, they're fairly light. Every picture I showed was a coin that was offered for auction for sale, at least in the last 10, 15 years. So there are auction houses that do it. There are restrictions on what you can import into the United States nowadays. Like, for example, a lot of those coins that I showed that had a crescent with stars that were minted in Bulgaria, you can't really import into the US now without doing a lot of paperwork and stuff like that. So it's not even worth the effort. Or else I would have grabbed that Earthshine one, but I just didn't want to.
Certified, right?
Yeah, that you have to prove that they had been outside of the country for a certain number of years. It's tough because, of course, when coins are minted, they're minted to travel. So like the restrictions on Egyptian coins, but that the laws don't care whether that coin was found in Egypt or found in the, in Great Britain, because that was also in the Roman Empire at the time.
One more question. You specified the coin about the transit of Mercury back 1118. So that means the transit of Mercury was known back then, or what?
Yeah, the 1189. By then, remember, this was the Islamic world where their astronomy and their math and their predictive ability was actually really good. And so they were able to predict these events, even if they weren't actually observable.
Yeah, right.
Oh,
okay. Yeah. Very good. Well, I'm a coin collector myself, so that's why.
Yeah. And that's the thing, is a lot of these events that are being commemorated, I mean, we look at things as that's cool from an astronomical or a visual perspective, but for them, a lot of it was the astrological meaning.
Mm-hmm.
Really good.
And very fascinating. Enjoyed that a lot. Thanks, Carl.
Thank you.
It's a good topic. And you actually own some of them. That's even better.
Next year it will be stamps. I'll see what I can do on stamps.
All right. Next up, we have Scott Harris. He's a planetary geologist for the Fernbank Science Center and the Jim Cherry Memorial Planetarium. He spent most of his 30-year career studying the record of asteroid and comet impacts on Earth. He's the author or co-author of more than 15 peer-reviewed papers and field guides and over 100 conference abstracts. Scott also studies extraterrestrial volcanism and the ancient history of our solar system preserved in meteorites. Through his outreach demonstrations, unique field trips, public lectures, and television appearances, especially developing and delivering original content for the planetarium, Scott draws on his active research program to engage students, teachers, and the community in an authentic science experience. He is currently the 2020 Outstanding Earth Science Teacher for Georgia, awarded by the National Association of Geoscience Teachers. Scott, it's all yours.
All right, thank you, Tim. And let's see if I can get this up. And does that come up okay?
Yes.
Good.
All right. Again, thank you. And I got involved with this last year because of Ken, so you can blame him for me being back to talk about things from a little bit of a different angle than many of you, but hopefully put some of the things that all of you do into some important context. And I actually, in being very busy with some of the planetarium things and our own line planetarium productions I do, and had missed the fact that Carolyn passed away yesterday, and I just wanted to, and so I put this on here just in because, as you'll see, one of the very first things I talk about, she's one of the co-authors. And I had the good fortune of being in the field with Gene back in 97, about a month before he went over to Australia and was killed. So a little bit of a twinge there for me. But what I want to talk about is the really the sort of symbiosis between the impacts on the moon and the impacts on the Earth and the Earth-Moon system, and bring that home a little bit in something that hopefully you'll enjoy, particularly perhaps Richard, because he's intimately a part of it, literally as we sit here. This is a little bit of chemistry here, not astronomy, but very relevant, because if I mention to most of you the term helium-3, these days, everybody throughout the astronomy world and even to the out on the street might actually say, "Oh, we're going to mine the moon," right? That's where that concept now is lodged. But of course, it is very important for geologists to be able to kind of piece together that again, that symbiosis between the astronomical record and what happens here on our planet. And just like the iridium that everybody thinks about with impacts, it is a very powerful tracer of extraterrestrial material, because the helium-3, for all practical purposes, is created by the sun, and helium-4, the more dominant species, is created by radioactive decay of uranium. So helium-3, when we have helium-3 anomalies in the seafloor sediment record, that kind of means something, and it's actually a little more more clear than the iridium record, because you can get into all kinds of things with the way iridium is transported through the geologic record and can accumulate without any meteoric particular enhancement. But this is where things kind of get started with a thought here. I'm going to carry through this with a record of the helium-3 to helium-4 ratios back in the what's called the late Eocene, about 36 to 35 million years ago. And that's very important to us here in Georgia, or very dear to us, because we have these beautiful tektites that are strewn across the southern coastal plain here, that then later was determined that they came from the Chesapeake Bay impact that occurred 35.5 million years ago, where you have the mouth of the modern bay in Virginia and Maryland today. Back in the mid-90s, Ken Farley, who is currently the principal scientist for the Perseverance rover, and along with Sandro Montanari and the Shoemakers, published an article that basically revealed this record and strongly suggested a cometary shower in the inner solar system that was responsible for this. because the notion was that it had to be comet shower or just influx of interplanetary dust, because helium-3 entering the atmosphere couldn't enter it there very dynamically because you would lose the helium. And so they had this sort of wafting mechanism of getting things down to the seafloor sediments. But then there's this sort of correlation between these big impacts like Chesapeake, also 100-kilometer diameter structure in Siberia called Popogai, that for all practical purposes were simultaneous. And the iridium spikes for those, the helium-3 spikes, all were kind of coincident. But then over the much broader region of the geologic record, over about a 3 million year period there's an overall enhancement, which still went to this, okay, maybe we've got some impactors coming in, but overall we've got interplanetary dust increasing, or we have a comet or comets coming in and doing that. But there was a little bit of a problem in, again, dynamically trying to figure out exactly what this meant in terms of the helium-3 source. Was it IDPs? Were there comets, as the Shoemakers and Kim were suggesting? Or was this an asteroid shower? And the reason asteroid showers became part of the discussion is because all these impacts that were being found geochemically were being tied to L and LL chondrites. And so it's like, what's the relation here? And finally, a rather ingenious compromise was published here with George Fritz and Raul Tagla and Natalia Adamiva, where they said, look, okay, we have a source of helium-3 that is not directly from the sun, not directly from IDPs, but guess where all that helium-3 is? We talk about with the mining in the regolith on the moon. So if you have an enhanced flux coming into the Earth-Moon system of asteroids, the moon's getting hit too. And so can we be deriving that helium-3 at much lower impact velocities from the moon, and then that ejecta basically raining down into the seafloor records? And that is where the reason for bringing all this up is to sort of establish this baseline of, that record you guys are looking at night, being this record of these potential storms that punctuate the geologic record, maybe going back, to the late heavy bombardment and beyond. But we're really kind of interested here in coming forward from that time in the relatively recent geologic record. And I was very familiar with that, working on the ejecta here in Georgia for a long time. And then I started working with Pete Schultz on the impact record in Argentina, where we have a number of glassy ejecta deposits. Some we've now been able to tie to potential craters. But they, while we were working on that, some of these people like Bill Bakke, that some of you may know, that I call sort of astromachinist, were able to do their wizardry and started looking at these asteroid breakups that were occurring, and again had this notion of the influx of IDPs into the inner solar system as a response to those breakups, or that dust. If you want to separate it from normal IDPs, you have an event, it gets all that dust in here, we get that record, doesn't require any big impactors or anything else. And so when when Ken and Bill and others published this in 2006, this is derived from their data. They were focusing on this breakup in the late Miocene, about 7 to 8 million years ago, with the Veritas asteroid group, or asteroid family. And they said, look, this has to be from the breakup and this dust coming in, because we don't have any record of impacts. Well, we looked at their data very carefully, and it's like, wait a minute, you've got a spike over here and a spike over here that correspond in time to these impact events we have a record of. And oh, by the way, we don't have a record in Argentina or any in South America of anything right at this spike of helium-3, but there is this lingering thing out there of this 56-kilometer Caracol crater in the middle of Central Asia that is somewhere around 5-7 million years. It's a little hard to figure out, but it has to be in that ballpark. So could we be seeing a similar type of shower that's in there as well? And so again, just the theme here is, do you have these fairly, I have to stop myself of saying regular, because that's what people then are drawn to, is periodicity. And forever people talked about trying to fit Napier and Klube and everybody else trying to figure out, is there some periodicity to these events? And kind of what we would say is, no, it's actually quite episodic. It's the worst case. It's like, oh, something goes bump in the night, sends things into chaos, and then we deal with that record. And when we, this is just a generalized thing, don't look too much at the details, but it kind of shows the some of the crater counting that is done on the lunar surface. And it appears that over time there are these sort of clusters. But the problem with interpreting these clusters as true clusters or storm events are secondary craters. Many of you may know that secondary craters are the bane of dealing with crater counting on the moon. And so it's easy to drastically overinterpret something like this, except to point out that where you see gaps, well, that's nothing. And that's real. That's a real nothingness. And so if you kind of interpolate the notion that the gaps are representative of where there are clusters, then you still get the notion that there might be these periodic storms that tend to correlate with some of the impact record that we see on Earth. And that, sort of makes sense. And it might mean that some of that geochemical record is out there. But is kind of still takes some people, even in the impact community, a little bit of gulp every time you deal with this, because the standard way that people have dealt with this for a long time is to have a nice curve of the impact flux in the Earth-Moon system that sort of is punctuated back at late heavy bombardment and then is nice and smoothly declining ever since. And so if you are in the business of trying to figure out time, but be a crater counting, every one of those little storms is kind of a pain to you. And so trying to figure out where they are and what they mean is sort of important to that, as well as the overall discussion of what the Earth-Moon system, what's going on astronomically in the Earth-Moon system has meant to life on our planet. And that kind of leads me to right now, which is, many of you have probably seen this before, but the current, while this is exactly current, this is LRO data from going from 2010 up to about 2016. So there's probably a one that's got more complete numbers on there. But this was, relatively small craters that have been observed by the LRO team through the first 2/3 of its mission. And the important takeaway here with all of these is that you can look at the numbers, but the predictions based on the flux curves that were available, it was significantly greater than what they predicted, which might just be, okay, well, we're dealing with big numbers and big errors, and you're getting good data. But it might also lead to at least the question of, are we actually getting a greater than the normal enhancement in the flux right now? And one of the things that actually is kind of buried in the supplemental data, or I think is actually in one figure in Ken's and the Shoemaker's paper back from '98, is while they concentrate on the Eocene, they show the data for the helium-3 for right now. And the highest helium-3 spike is right now in the last 60 million years. And the explanation for that usually is, well, that has to do with how that material is processed in the sea sediments. It doesn't really mean anything. But then ultimately, we just really don't know. And so it might be that we are do have an enhancement by maybe relatively small impactors, and or just general dustiness in the inner solar system. But again, the theme here is just that we have have a record of these episodic storms and the potential that, and not just the potential, I guess, but the certainty that they will continue into the future. But then to kind of bring this back home, literally to, as I mentioned, Richard, a group out of Japan last summer, during the middle of the pandemic, published a paper in Nature Communications using Cayuga data that some of you have shown here in the conference. It's very high resolution data, and they went through and studied about almost 60 craters here, and they found 8 of them, including Copernicus, that all have statistically identical crater counting surface ages. And I'll just flash that up there briefly just to see what some of these tend to look like. The curves they interpreted as essentially being the same. And so they concluded that the only way to explain that was to have 800 million years ago a storm. And so that would be the first significant storm after essentially late heavy bombardment that is noted clearly in the lunar record. But the fun part of this for me and those several of us here in Georgia and over on my geology side where do impact petrology is when they did this calculation and model, they predicted what the flux on Earth would be for the same time and said that there should be enough mass that there would be 1 or 2 Chicxulub scale craters somewhere out there at this time in the Earth record. And we basically said, we have one. And so if you look at this is Copernicus, formed 800 million years ago. And this is a relief map of Georgia. And I kind of invite you to see if you see a partner for Copernicus. And I will draw your attention over to this area where for decades and decades, Appalachian tectonic geologists have looked at this with fascination as a very old terrain and imagined mountains rising here higher than Everest in a range out ahead of the Appalachians that most people think about here that were last modified during the Alleghanian orogeny 300 million years ago. And we would say now that no, this is not the root of a big mountain range out here. This is actually an exhumed structure. And the proof, well, is not that. This is the very center that looks kind of like a bowl. Don't be fooled by the bowl, although it probably is related. When you go outside of that bowl into the surroundings, you find some interesting things. And just as a reminder, some of you have probably seen things like this before, but these are good shocked quartz grains from various known impacts like Chicxulub and Wetumpka near us here in Georgia and Alabama. All these little lines, they are produced by the compressive shock forces of the impact. And they come in different varieties, some which are kind of decorated with little bits of fluid, typically water and CO2. These are from the Rochechouart impact in France. But here you go. And we have beautiful decorated shock quartz here. And this, some years ago, I would say, well, I had some grains. But the pandemic allowed a great deal of field work to be done where we were able to find copious amounts of rock that is inside a melt. So there's a melt and then pieces of the target material in it, and it's the target material that is extensively shocked. And that material is not in this bowl, but is in the melt out here. And that melt is mapped all the way to the Alabama line. And further field work showed that there's deformation, lower scale deformation than what produces those little lines in other areas of this mountainous terrain, again, leaving ultimately an ellipse that, in order to accommodate the melt and the deformation, looks like that. And if you kind of compare that to things like that, some of you looked at, particularly Schiller there on the moon with your own eyes, there would be a debate right now whether we're looking at, there's always a debate about these, whether you're looking at something very oblique between 10 and 15 degrees, or you're looking at something breaking up. And so we're kind of in that discussion, but I want you to note these medial ridges that develop on these and the similarity with the shock deformed areas I was showing you in this structure. And this is Schiller superimposed or underneath the structure in Georgia with it superimposed, and they're almost identical in size. And so a lot of people said, okay, well, if you have a crater, is this just a deformed, did this used to be a big circle, maybe 80 kilometers or 80 to 100 kilometers across, that then was deformed by the geologic forces, the tectonism? And we've said, no, everything is consistent with the level of deformation, with this simply being a structure very much like Schiller with a medial ridge complex rather than a central uplift, a central single peak. And again, the important concluding thing here is its age. And we're able to go into the melt rock here that has pieces of target in it, but this is the melt. And Stephen Jarrett, a colleague of mine with the American Museum of Natural History, formerly of DeKalb County here in Georgia as well, uses zircons to date these, and the youngest zircons that we interpret crystallizing from that melt are exactly 800 million. And so we think this, is part of the, part of this storm. And if that's not cool enough, with no pun in, well, probably with a pun intended there with the word cool. At the same time we were working on this, and the Cayuga group was working on their data, a group at MIT published some computer models that basically said that to get us into the last snowball Earth about 800 million years ago, that the only way to really do it to support the geologic record that's out there is for the solar insolation to decline extraordinarily rapidly. And they immediately suggested volcanoes and completely neglected mentioning impacts at all. But there are actually 2 or 3 sources of material involving the extraterrestrial record that could lead to this. One is having large impacts like I showed you on Earth, but more importantly, all of those larger scale impacts, 20 kilometers or so and up to Copernican size on the moon, again, producing that helium-3 laden dust, with the important part being there, not the helium-3, but just the dust. And either the progenitors to those objects coming in, increasing the dustiness and the opacity of the inner solar system, or kicking up stuff from the moon, or hitting Earth, or likely all 3, then could lead us into that last major huge climate issue before we get into the mundane things of the last 500 million years. So with that, I will thank you for your attention. And again, Richard is right on the very, very northeastern corner of that structure I showed.
I want to let everybody know that Scott did this presentation at the last meeting of the local Charlie Elliott Astronomy Club, and it is recorded. The entire talk goes on, what was it, an hour and a half?
Yeah, but that covers a lot more than just this.
Right, and that is recorded, and I guess you can make that talk available online if anybody wants to see the very expanded version of it. It's very interesting.
Yes. Scott, Richard,
Yes.
How big do they think this object was that hit the Earth?
Well, the calculations that we had. So 2 things. When you say they, I mean we. So the they there would be what amount of material is out there, and I don't have the number in front of me for the amount of mass that would be calculated based on the lunar record to expect. But again, their conclusion was that you would have enough material to have 1 or 2 Chicxulub scale structures, or 150 to 200 kilometer structures, and then a smattering of smaller ones. If you take this, it doesn't really matter whether you take this object and the object that would form the structure we see, regardless of whether you're talking about very low angle or you're talking about something at a slightly higher angle breaking up. The basic parameters end up being the same, so that you end up with the lowest I've been able to put it is at about a 28 kilometer diameter object, and the highest is about a 35 kilometer diameter object.
That's huge. Wow. That's huge. Huge.
Wow. To make a crater of a given size, does it require a larger asteroid on the Earth as compared to on the Moon due to Earth's larger gravity?
Other way around, actually. But for all practical purposes, it's the same. It's same ballpark. They're within very little of each other. I mean, you've got a greater gravity on Earth, so you actually have in principle, a smaller object could make something that is that's bigger if you get into gravitational collapse. But the unknown here is the velocity. And so the velocity is mattering a whole lot more than most everything else. So you do get it. The interesting part of this, the discussion here that I won't get too deep into, which goes back, if any of you have kept apprised of the recent literature on Copernicus, is, are these asteroids or comets or centaurs or, large carbonaceous bodies.
Right.
So there is some interesting puzzles to be worked out there.
Have they figured out the size of the object that created meteor crater in Arizona?
Say that again, Ken.
Have they calculated possibly the size of the original object that created meteor crater in Arizona?
Yeah, I mean, it depends on whose model you look at, but I mean, it's generally something around a third to half of a football field, so 30 meters or so.
When there are meteor showers, the Earth and the Moon are going through the tail, not the tail, but the remnants of these comets. And people have seen these objects hitting the Moon. Those would be small things, but is it possible that some of those are maybe a little larger?
Right. I mean, it's always, that's even a question that was posed back, I think it was a year or two ago, right? There's conventional wisdom is that something even like the Tunguska body, right, might be associated with Comet Inky.
Mm-hmm.
Right, and so there, I know that Peter Brown actually kind of did a campaign trying to survey during the Beta Taurids, trying to see if there were larger objects out there, because they had calculated that we might be encountering a part of the stream where if there were larger ones there, that you could see them. So there's always that possibility that there's a chunk of some of these larger things that gets left out there, and then then that's one of the questions we always run into with any of these notions is, what's the residence time of these collisions? I mean, most of the stuff is probably going to be swept up fairly quickly in geologic time. Well, the
Leonids, about every 33 years, have a big shower. I remember here in Maryland in 1966, I got up about 5 o'clock in the morning. I was counting about 5,000 an hour. And that wasn't the peak. The peak was like 25,000 an hour out around Arizona. So that might have had some larger pieces in it.
Scott, Julian Parks here.
Hey, Julian.
Hey, how you doing? As the Earth revolves around the galaxy, is there evidence on the Earth and the Moon of bombardment increases at certain points in the galaxy?
There have been people who have tried to make that claim, but most of the people in the impact community I know stay well away from that argument. Just not so much to say, hey, it's not an interesting hypothesis. It's just that we rather come at it from the, most of us are geologists who come at it from the observational end and say, let's establish what the record actually is, and then and go from there. But there have been people who have tried to run the computer models about what the gravitational influences would be for essentially galactic tides, and come up with these notions that really are, the bad part is they're kind of untestable.
Right.
But that's where, hopefully more analyses will be done on that aspect of crater counting that is able to establish on the Moon and maybe Mercury and other surfaces where you have true clusters, where it can be demonstrated that it's statistically how you have to have a shower, and then that makes it interesting for us on Earth and eventually on Mars and maybe a few asteroids, in kind of looking for the record of that material at the right time to see if that can substantiate it.
Thanks.
Thank you, Scott. Great talk.
All right, if there's no further questions, Scott, I want to thank you again for the presentation. All right, up next with our closing remarks, Carl Hergenrother, the new Executive Director of the Association of Lunar and Planetary Observers.
I'd like to thank everyone who joined us for the last 2 days, everyone who gave talks, presentations, as well as those listening. I mean, the ALPO would be nothing without everyone's contributions, whether that's simply being a member or contributing observations. I mean, as a kind of citizen science volunteer effort, we really can't exist without participation and members. One of the nice things about, focusing on the solar system is a lot of the issues that are kind of affecting the rest of astronomy, we're a little bit immune to. We observe bright objects that can be seen no matter what your light pollution is, that can be seen through smoke and haze, objects that are extremely interesting, very dynamic, that, we have spacecraft at a lot of planets now. There always seems to be spacecraft at Mars. There's quite often one at Jupiter, at Venus, but we don't have weather satellites. We don't have constant 24/7 monitoring of these bodies with spacecraft. So doing backyard astronomy of the planets, and this includes comets as well, which are very dynamic, and there's, at any one time, there's many, many dozens of them available. In a way, we, the amateur community, are the kind of first responders to new things that are happening on these bodies. We're the ones who detect new storm outbreaks. We're the ones who detect new cometary outbursts and splitting events. So the service, in a way, that the amateur community provides isn't just, for our own benefit and enjoyment, which of course we all do it because we enjoy it, but we really are helping further the science. And I think that's something that we shouldn't lose track of. So I thank everyone for coming for this year's conference. I hope we can meet somewhat in person next year. Maybe we'll even do kind of a hybrid approach where we'll have an in-person meeting, plus we'll also stream the meeting live on the internet. But I want to thank everyone again.
Great to be here.
Thank you.
Thanks, Carl. And I also want to remind everybody that in approximately 2 hours, 23 hours Universal Time, 7 o'clock Eastern, 4 o'clock Pacific, we will have our awards presentations, the door prizes, and keynote speaker with Damian Peach. And also let everybody know that this conference has been simulcast on our YouTube channel. And I want to thank the people over on YouTube that have been participating. We have averaged about 25 people a day on our YouTube channel, which is very nice. And we've averaged about 64 people a day on our Zoom call. So thanks for everybody that attended. Like I said, the YouTube channel will keep both days of the conference. If you ever want to go back and watch or listen to any of the talks, they will be available on our YouTube channel, as well as the keynote speech tonight. It'll also be simulcast if you're interested and tune in on that. I will be sending out a link for the awards and the keynote speakers in a few minutes to everybody on the email list. So I again want to thank everybody for being here.
Thank you. Great job, Tim.
Thank you, Tim.
Thank you, everyone.
Thanks, Tim.
All right, see you guys later.
Okay, bye.
Thank you for a great
everyone.
program.
Thanks much, guys.
Bye-bye, everyone. And yes, thank you, Tim, for throwing this all together and keeping us all on schedule.
Tim, the link will still be the same when we come back at 7 o'clock, in a couple hours.
I will be sending out a new link.
New link. Okay.
Yes.
All right. See you later. Thank you.
All right. Joanne, did you have a question?